Hello there, and welcome to the Sleepy Science Place. I'm so glad you found your way here tonight. Maybe you've had a long day filled with rush and noise, or maybe you're simply the kind of person who finds comfort in the slow unfolding of natural wonders rather than counting sheep in endless loops. Either way, you've arrived at exactly the right place, and tonight's journey is designed just for you. Outside your window right now, whether you can see it or not, the atmosphere is doing something remarkable. It's breathing, shifting, dancing in ways both invisible and magnificent. Clouds are forming and dissolving. Winds are carrying stories across continents. Temperatures are rising and falling in ancient rhythms that predate every civilization, every language, every human thought. The weather, this ever-present companion of ours, is quietly performing miracles, and tonight we're going to explore some of the most soothing, wonderful facts about weather and climate that science has uncovered. Before we begin our gentle drift through rain and wind and the patient turning of seasons, I want to invite you to get truly comfortable. Adjust your pillow. Let your shoulders drop away from your ears. There's nowhere you need to be, nothing you need to do. If you're enjoying this journey and you'd like more like it, consider subscribing and letting the algorithm know that calm content matters. But truly, there's no pressure. You're here now, and that's what counts. Tonight, we'll wander through facts about snowflakes and thunder, about the way sunlight bends through raindrops, about winds that circle the planet and temperatures that rise and fall like the breathing of something vast and alive. We'll talk about clouds that form in the stratosphere and rain that never reaches the ground. We'll explore the gentle science of dew and frost, the patient architecture of ice, the ancient memory locked in glaciers. These aren't just facts, they're invitations to wonder. They're reminders that you live on a planet wrapped in an atmosphere so complex and beautiful that scientists are still discovering new things about it every year. And all of this is happening right now, right above you, whether you're awake to witness it or drifting peacefully into sleep. So settle in. Let your breathing slow. And let's begin this quiet exploration of the most relaxing facts about weather and climate, the perfect companions for falling asleep. Let's start with something you've probably heard before but perhaps never really considered. No two snowflakes are exactly alike. This isn't just poetic language, it's mathematical truth. Each snowflake forms around a tiny particle of dust or pollen high in the clouds, and as it falls through different layers of the atmosphere, it encounters varying temperatures and humidity levels. These conditions shape the ice crystal in utterly unique ways. The path each snowflake takes through the sky is different, even if only by inches, and those tiny differences create infinite variety. Trillions upon trillions of snowflakes have fallen throughout Earth's history, and each one, each delicate, six-sided wonder, has been an original, a singular expression of frozen water that has never been repeated and never will be again. There's something deeply comforting about that, isn't there? The idea that nature isn't interested in mass production, that even in something as common as snow, there's room for endless creativity and individuality. And speaking of snow, here's something that might surprise you. Snow doesn't actually fall silently. We think of snowfall as quiet, and in a way it is, but snow crystals do make sound when they land. It's just that the sound is so soft, so gentle, that human ears can't detect it. Scientists using incredibly sensitive microphones have recorded the tiny acoustic signatures of snowflakes touching down on various surfaces. Each landing creates a minute vibration, a whisper too quiet for us to hear. But beyond that, fresh snow also absorbs sound. The spaces between snowflakes trap sound waves, dampening ambient noise. That's why a freshly snow-covered landscape feels so peaceful. It's not just the visual softness, it's the actual acoustic quality of the environment. The world becomes muffled, gentler, wrapped in a blanket that absorbs harshness. When you walk through fresh snow and everything feels hushed and sacred, you're experiencing real physics, the sound-absorbing properties of accumulated ice crystals working to create that peaceful atmosphere. Now let's drift upward for a moment, into the clouds themselves. Clouds are essentially floating rivers. A single cumulus cloud, one of those puffy, cotton-like clouds you see on pleasant days, can contain the same amount of water as 10 full swimming pools. That's roughly 500,000 pounds of water, suspended in the sky, held aloft by updrafts of warm air. The water exists as countless tiny droplets, each one so small and light that it floats rather than falls. These droplets form around microscopic particles called cloud condensation nuclei, dust, sea salt, even bacteria, and they remain suspended until they grow heavy enough to precipitate. What's remarkable is that clouds are constantly forming and dissolving, constantly in flux. The cloud you're looking at now isn't the same cloud it was 5 minutes ago. Water is evaporating from its edges even as new droplets form in its center. Clouds are processes, not objects. They're verbs pretending to be nouns, actions frozen in what only appears to be stillness. There's a phenomenon called virga that you may have witnessed without knowing its name. Virga occurs when rain or snow falls from a cloud but evaporates before reaching the ground. You'll see it as dark streaks descending from the base of a cloud, precipitation falling through a shaft of sky, dissolving into dryness before it can complete its journey. It's rain that never arrives, snow that melts in midair. In desert regions, virga is quite common. The air near the ground is so hot and dry that falling precipitation simply can't survive the descent. There's something achingly poetic about virga, something that speaks to efforts that don't quite reach fruition, to gestures made nonetheless. The cloud tries to offer rain to the ground below, and even though the gift evaporates before arrival, the attempt was real. The falling began. The intention manifested. And in that attempt there's a kind of beauty, incomplete, yes, but genuine and graceful in its incompleteness. Here's a fact that might change how you think about rainbows. What you're seeing when you look at a rainbow isn't actually a thing or an object. A rainbow is an optical phenomenon, which means it's an interaction between light, water, and your specific position. The rainbow you see is unique to you. Someone standing even a few feet away is seeing a slightly different rainbow, one created by light refracting through different water droplets at different angles. You can never reach a rainbow because it's not located anywhere in particular. It's not a destination. It's a relationship between sunlight, moisture, and your precise point of observation. Two people can never see exactly the same rainbow, even if they're standing side by side. Each of you is looking through slightly different droplets, positioned at slightly different angles, creating two similar but distinct optical events. You are always at the center of your own rainbow, always exactly the right distance away. It's a phenomenon that exists because you're there to witness it, a collaboration between physics and perception that creates something that seems solid, but is actually made of nothing but light and geometry. And while we're discussing light and water, consider this. The blue color of the sky isn't actually blue. The sky has no color of its own. What you're seeing is the result of a process called Rayleigh scattering. Sunlight is composed of all colors, all wavelengths of visible light traveling together, and when that light encounters the molecules in Earth's atmosphere, it scatters in all directions. Blue light has a shorter wavelength than other colors, which means it scatters more easily and more extensively. So when you look up at the sky during the day, what you're seeing is blue light that has been scattered by nitrogen and oxygen molecules, bouncing around the atmosphere until it reaches your eyes. The sky is every color and no color, a canvas that reveals blue only because of the particular way light interacts with air. At sunset, when the sun is lower and its light passes through more atmosphere, the blue scatters away entirely, and the longer wavelengths, reds, oranges, pinks, finally reach your eyes, painting the horizon in warm tones. The sky is performing color theory in real time, demonstrating physics with every sunrise and sunset. Let's talk about dew for a moment, those tiny droplets that appear on grass and leaves in the early morning. Dew forms through a process that feels almost magical. During the night, surfaces like grass blades radiate their heat away into the sky. As they cool, they eventually reach what's called the dew point, the temperature at which the air immediately surrounding them can no longer hold all its water vapor. The vapor condenses directly onto these cool surfaces, forming droplets. What's lovely about this is that dew doesn't fall from the sky. It appears, forms in place, materializes out of seemingly nowhere. One moment the grass is dry, the next it's jeweled with water. Dew is a quiet demonstration of the atmosphere's generosity, the air releasing moisture it no longer needs, offering it back to the earth in countless tiny gifts. Those droplets catch the morning light and hold it, turning an ordinary lawn into something that glimmers, something temporarily precious. And then, as the sun rises and warms everything, the dew evaporates, returning to the air, completing the cycle, waiting to descend again when conditions allow. Lightning is one of nature's most dramatic displays, and yet the facts about it are somehow even more impressive than the experience of watching it. A single lightning bolt can heat the air around it to approximately 30,000 Kelvin. That's 5 times hotter than the surface of the sun. This happens in a fraction of a second. The air molecules are heated so rapidly and so intensely that they don't have time to expand in an orderly way. They explode outward, creating a shock wave that we hear as thunder. And here's what's remarkable. You're hearing the sound of air being superheated and then rapidly cooling, a sonic record of one of the most energetic events in weather. The reason thunder rumbles rather than simply making a single sharp sound is that different parts of the lightning bolt are at different distances from you, so the sound arrives at slightly different times, creating that rolling, tumbling quality. Lightning also creates nitrogen compounds that fall to earth and fertilize soil, meaning that in addition to being spectacular, lightning is actively contributing to plant growth. Storms aren't just destruction. their renewal, redistribution, a violent form of nourishment. Clouds exist at many different altitudes, and some of the highest are called noctilucent clouds. These form at the edge of space, roughly 50 miles up in the mesosphere, where the air is incredibly thin and cold. They're composed of ice crystals so fine that they're only visible during twilight, when the sun has set at ground level but still illuminates these high-altitude clouds from below. They glow with an eerie, electric blue light, rippling and undulating like waves on a cosmic ocean. Noctilucent clouds are the highest clouds in Earth's atmosphere, existing in a region where atmospheric pressure is less than 100,000th of what it is at sea level. They're so delicate, so rare, that scientists are still studying what conditions allow them to form. Some research suggests they may be increasing in frequency due to climate change, as certain pollutants can provide the nucleation sites needed for ice crystal formation. They're beautiful accidents, perhaps, or beautiful warnings, displays of ethereal light appearing at the very edge of where Earth's atmosphere meets space. The concept of a raindrop shape that most of us carry in our minds, teardrop-shaped, pointed at the top and round at the bottom, is actually inaccurate. Real raindrops in free fall are shaped more like hamburger buns, rounded on top and slightly flattened on the bottom due to air resistance. Very small raindrops, those under a millimeter in diameter, are nearly spherical because surface tension dominates. Larger drops become increasingly flattened as they fall, with air pressure pushing up against their bottom surface while the top remains more rounded. And if a raindrop gets too large, more than about 4 millimeters in diameter, it becomes unstable and breaks apart into smaller droplets. There's a maximum size to raindrops, a limit imposed by the physics of falling water, and nature respects that limit. Every drop of rain that lands on your skin has self-organized into one of these shapes, responding to forces invisible but absolute, finding its form in the fraction of a second between cloud and ground. Fog is just a cloud that has decided to visit the surface. There's no fundamental difference between fog and clouds. Both are composed of tiny water droplets suspended in air. The distinction is purely about altitude. Fog forms when air near the ground cools to its dew point, causing water vapor to condense, or when warm, moist air moves over a cold surface. What's enchanting about fog is how it transforms familiar landscapes into mystery. Distances become uncertain. Sounds behave strangely, sometimes muffled, sometimes carrying farther than they should. Objects appear and disappear. There's a softness to fog, a gentleness that makes the world feel smaller and quieter. In thick fog, visibility can drop to just a few feet, creating a private sphere around you. You exist in a small bubble of visible space, everything beyond it rendered into white or gray suggestion. Fog is the atmosphere at its most intimate, pulling the world close around you, insisting on slowness, on attention to what's immediately present rather than what's distant. And then it lifts, dissolves, releases everything back into clarity, as if granting permission for the world to be large again. Wind is the atmosphere attempting to achieve balance. Air pressure differences create wind. Air flows from areas of high pressure to areas of low pressure, trying to equalize the imbalance. But because Earth is rotating, winds don't travel in straight lines. Something called the Coriolis effect causes moving air to curve, creating the swirling patterns we associate with weather systems. In the northern hemisphere, winds spiral counterclockwise around low-pressure systems and clockwise around high-pressure systems. In the southern hemisphere, it's the opposite. These spirals are visible from space when you look at satellite imagery. Hurricanes, cyclones, typhoons, all spinning in their respective directions, following rules imposed by planetary rotation. What's beautiful is that wind is invisible cooperation, molecules of air passing energy along, each collision creating movement, each movement creating weather. The wind that touches your face has traveled, perhaps from across an ocean, carrying with it the temperature and moisture of distant places, connecting you to regions you've never seen. The jet stream is a river of air flowing high in the atmosphere, typically between 30,000 and 40,000 feet. These are fast-moving currents of wind, sometimes exceeding 200 miles per hour, that flow from west to east, meandering across continents like aerial rivers. Jet streams form at the boundaries between cold polar air and warmer air from lower latitudes, where the temperature difference creates pressure differences that drive these powerful winds. Commercial aircraft often use the jet stream to speed up eastbound flights, essentially riding the current like a boat floating downstream. A flight from Los Angeles to New York might be 30 to 45 minutes faster than the return journey, simply because of the jet stream's push. But more than that, the jet stream influences weather patterns across entire continents. When it meanders far to the north or south, it can bring unusual weather, cold snaps, heat waves, prolonged dry spells, or extended rainy periods. It's a reminder that weather isn't local, that what happens thousands of miles away and several miles up can determine whether you'll need an umbrella tomorrow. The jet stream is connection made visible, a demonstration that the atmosphere is one coherent system, breathing and flowing as a unified whole. Snowflakes don't just fall, they also dance. As a snowflake descends, it tumbles and rotates, carried by air currents, buffeted by winds, taking a chaotic path toward the ground. This tumbling motion is part of what makes each snowflake unique. As it rotates, different parts of the crystal are exposed to different conditions, causing it to grow asymmetrically. But here's what's wonderful. If you watch snow falling in still air, you'll notice that it doesn't fall straight down. Snowflakes flutter and drift, swaying back and forth, performing a gentle aerial ballet. This happens because of their shape. The flat, branching structure catches air, creating drag and lift, causing the snowflake to tilt and glide. Falling snow is quieter than rain, softer, more hesitant, as if each flake is reluctant to complete its journey, taking its time, making the descent last as long as possible. There's no rush. Gravity is patient. And so the snowflakes dance their way downward, turning a simple physical process into something that feels choreographed, intentional, graceful. Hail is one of weather's stranger creations, balls of ice falling from the sky during thunderstorms, sometimes small as peas, sometimes large as grapefruits. Hail forms in powerful thunderstorm clouds where strong updrafts carry raindrops high into extremely cold regions of the cloud. The drops freeze, then fall, then get caught in another updraft and carried up again, accumulating more layers of ice with each trip. If you cut a hailstone in half, you can see these layers, like the rings of a tree, each one representing a journey up and down through the storm. Some hailstones make multiple trips before finally becoming heavy enough that the updrafts can't lift them anymore, and they fall to the ground. The largest hailstone ever recorded in the United States was nearly 8 inches in diameter, about the size of a volleyball, and weighed almost 2 pounds. It fell in South Dakota, the result of a storm so powerful that it could repeatedly lift nearly 2 pounds of ice high into the atmosphere. There's something almost absurd about hail, something that seems to violate the natural order. Ice falling from the sky in summer, during the warmest months, proof that the atmosphere contains multitudes, that cold and heat can exist in the same storm system, separated by altitude, creating conditions bizarre enough to manufacture ice from summer rain. The smell of rain has a name, petrichor. It's created by a combination of things: plant oils that accumulate on surfaces during dry periods, compounds released by bacteria in the soil, and ozone carried down from the upper atmosphere by downdrafts. When rain finally falls after a dry spell, it disturbs these accumulated substances, releasing them into the air, creating that distinctive earthy, fresh, somehow nostalgic scent. Petrichor is technically a chemical signature, but it feels like something more, like the earth exhaling in relief, like nature's way of marking the transition from drought to moisture. The smell is strongest after the first rain following a dry period, when the accumulated oils and compounds are most concentrated. It's ephemeral, fading as the rain continues, as the substances are washed away or absorbed. But in those first moments, when the rain begins and that scent rises, there's a quality of renewal, of something returning, of balance being restored. Petrichor is proof that we don't just see and hear weather, we smell it, we sense it with our whole body, integrated into the environment, part of the same system that creates clouds and wind and precipitation. Frost doesn't form the way you might think. It doesn't begin as water that freezes. It forms directly from water vapor in the air, skipping the liquid stage entirely. This process is called deposition, and it happens on cold surfaces when the air temperature drops below the dew point and below freezing. Water vapor molecules in the air come into contact with the cold surface and immediately transform into ice crystals. These crystals grow into intricate patterns, feathers, ferns, flowers, each one following rules of crystalline structure, creating art from physics. Frost is ephemeral architecture, temporary cathedrals built of ice, impossibly delicate, vanishing as soon as the sun touches them. On very cold mornings, you'll find frost covering everything: grass blades, car windshields, leaves, spiderwebs, and each surface becomes a canvas for these spontaneous ice sculptures. What's remarkable is that frost is organized chaos, randomness producing pattern, order emerging without instruction. The ice crystals follow the laws of molecular bonding, arranging themselves in geometries that happen to be beautiful, as if beauty were simply a side effect of following natural law. Rainbows sometimes appear in pairs, a primary rainbow and a fainter secondary rainbow above it. The secondary rainbow is created by light that reflects twice inside raindrops before exiting, rather than just once. This extra reflection reverses the order of colors. In the primary rainbow, Red is on the outside and violet on the inside. But in the secondary rainbow, violet is on the outside and red on the inside. The region between the two rainbows is noticeably darker than the sky around them, and this dark band is called Alexander's Band, named after Alexander of Aphrodisias, who first described it in the 2nd century. In that dark band, light is being refracted in ways that don't reach your eyes, creating a shadow in brightness, a zone of relative darkness between two arcs of color. Double rainbows are rarer than single ones, requiring specific conditions of sunlight angle and rain distribution. But when they appear, they're breathtaking. Two complete arcs of refracted light, framing a band of darkness, demonstrating that light and shadow are always partners, that you can't have illumination without contrast, brightness without a reference point for what brightness means. You're doing beautifully. There's no hurry, nowhere else you need to be. Let your body sink a little deeper into whatever's supporting you. Notice your breathing if you'd like, but don't try to change it. Just let it happen, in and out, as automatic as weather, as reliable as seasons. The facts will continue, gentle and steady, waiting for you whether you're fully awake or drifting at the edges of sleep. Everything is exactly as it should be. Rest if you need to. Listen if you'd like. There's no wrong way to do this. The weather outside continues its work. Clouds forming, winds moving, temperatures shifting, and you're safe here, learning about it all, letting the knowledge wash over you like rain on a window. Take your time. We'll be here when you're ready. Clouds are classified into different types based on their altitude and appearance, and each type has a distinct personality, if we can anthropomorphize weather for a moment. Cirrus clouds are high and wispy, made of ice crystals, stretched thin across the sky like brushstrokes. They often precede a change in weather, appearing a day or so before a storm system moves in, as if announcing what's coming. Cumulus clouds are the puffy, cheerful ones, cotton balls piled up in fair weather, marking thermals, rising columns of warm air. Stratus clouds are low and gray, blankets pulled across the sky, often bringing drizzle or light rain. Nimbus clouds are the rain makers, dark and heavy with moisture, sometimes towering miles into the atmosphere. And then there are the rare and spectacular ones. Mammatus clouds with their pouch-like protrusions hanging down. Lenticular clouds that form over mountains and look like UFOs. Noctilucent clouds glowing at the edge of space. Each cloud type is a chapter in the atmosphere's ongoing story, a signal about what's happening with temperature, moisture, and pressure. Learning to read clouds is like learning a language. The sky is speaking, always, telling you what's happening and what's likely to happen next. Thunder and lightning are two parts of the same event, but they travel to you at different speeds, which is why you see the flash before you hear the rumble. Light travels at roughly 186,000 miles per second, so you see lightning essentially instantaneously. Sound travels much slower, about 767 miles per hour at sea level, or roughly 1 mile every 5 seconds. So if you see lightning and then count the seconds until you hear thunder, you can estimate how far away the lightning struck. 5 seconds equals 1 mile. 10 seconds equals 2 miles, and so on. This is a little game you can play during storms, a way of measuring distance using nothing but your senses and a bit of arithmetic. But what's soothing about this is the reminder that storms have structure, that even dramatic weather follows predictable rules. The lightning reaches you first because it must, because physics demands it. The thunder follows, patient, inevitable, announcing what has already happened. And if you're inside, safe and dry, there's something deeply comforting about experiencing a storm this way, counting the seconds, tracking the distance, participating in the storm without being endangered by it, connected to the weather but protected from its intensity. Temperature is essentially molecular motion. When something is hot, its molecules are vibrating or moving quickly. When something is cold, its molecules are moving more slowly. At absolute zero, negative 459.67 degrees Fahrenheit or 0 Kelvin, molecular motion would theoretically stop completely, though achieving absolute zero is impossible in practice. This means that temperature is really a measure of energy, of activity at the atomic level. When you feel warmth from sunlight, you're feeling infrared radiation exciting molecules in your skin, making them vibrate faster. When you feel cold, you're losing heat energy to the surrounding air, your molecules slowing down as energy transfers away from you. There's something profound about this. The lived sensation of warmth or cold is actually the experience of molecular motion, of countless invisible particles moving at different speeds. You're not just experiencing weather. You're experiencing physics at the most fundamental level, feeling atoms dance or slow, sensing the energy state of matter. Every temperature is a story about motion, about energy flowing from one place to another, about the universe's constant attempt to distribute heat evenly, to achieve equilibrium, a goal it will never fully reach because stars keep burning, planets keep rotating, and energy keeps flowing. The water you drink today has been cycling through Earth systems for billions of years. The water molecules in your glass might have been part of a cloud over the Pacific Ocean last month, part of a glacier in Antarctica last century, part of a dinosaur's blood 150 million years ago. Water doesn't get created or destroyed. It cycles endlessly through the atmosphere, oceans, rivers, glaciers, and living things in a process called the hydrological cycle. Water evaporates from oceans and lakes, rises into the atmosphere, condenses into clouds, falls as rain or snow, flows into streams and rivers, returns to the ocean and begins again. The same water over and over, cycling through different forms and locations but never lost. This means that in a very real sense, water connects you to the entire history of Earth. Every raindrop is ancient. Every cup of water you drink is composed of molecules that have witnessed eons. The hydrological cycle is one of Earth's most fundamental patterns, a loop that has continued since the planet had enough atmosphere to support liquid water, and it will continue long after human civilization is a distant memory. There's something both humbling and comforting about that. We're participants in a cycle vastly larger and older than ourselves, temporary stewards of water that belongs to no one and everyone, to no time and all time. Hurricanes are powered by warm ocean water, requiring sea surface temperatures of at least 80 degrees Fahrenheit to form and sustain themselves. As warm, moist air rises from the ocean surface, it creates an area of low pressure beneath it. More air rushes in to fill that low-pressure area. Then it also warms and rises, creating a cycle. The rising air cools as it ascends, and its moisture condenses into clouds, releasing heat energy, lots of it. This heat makes the air rise even faster, pulling more air in at the surface, creating stronger winds which evaporate more water from the ocean, which adds more moisture and energy to the system. It's a feedback loop, a self-reinforcing cycle that can create winds exceeding 150 miles per hour in the strongest storms. But here's what's interesting. Hurricanes also serve a purpose. They're part of how Earth distributes heat from the tropics toward the poles. Without hurricanes and their cousins, typhoons, cyclones, the tropics would be even hotter and the poles even colder. Hurricanes are destructive, yes, but they're also mechanisms of balance, part of the planet's climate regulation system. They're not aberrations or malfunctions. They're features of how Earth maintains equilibrium. Violent expressions of the atmosphere's attempt to achieve balance, to share energy, to prevent extremes from becoming more extreme. Temperature records are made to be broken, but some are more remarkable than others. The highest reliably recorded temperature on Earth was 134 degrees Fahrenheit in Death Valley, California, in 1913. The lowest was negative 128.6 degrees Fahrenheit at the Soviet Vostok Station in Antarctica in 1983. That's a range of more than 260 degrees, an extraordinary testament to the diverse conditions Earth's surface can support. But temperature extremes happen in small scales too. The air temperature might be mild, but step from shade into direct sunlight and you feel a dramatic change. The ground surface can be much hotter than the air above it, which is why walking barefoot on asphalt in summer is painful. Deserts experience wild temperature swings between day and night, scorching during the day, freezing at night, because dry air doesn't hold heat well. Meanwhile, humid coastal areas have much smaller temperature ranges because water vapor stores heat energy. All of this is the atmosphere demonstrating its complexity, creating microclimates and local variations, proving that weather isn't uniform but textured, full of gradients and boundaries, transition zones where different air masses meet and interact. The term Indian summer refers to a period of unseasonably warm, dry weather that sometimes occurs in autumn, typically in late September through November in the Northern Hemisphere. The origins of the term are uncertain and somewhat disputed, but the phenomenon itself is real and can be explained by atmospheric patterns. Indian summer happens when a high-pressure system stalls over a region, bringing clear skies, light winds, and warm temperatures, essentially summer-like conditions appearing after the first frost or after autumn weather has clearly begun. There's something almost melancholic about Indian summer, a brief reprieve, a last gift of warmth before winter's inevitable arrival. The trees may already be changing color, leaves beginning their cascade to the ground, and yet the air is warm, the sun generous, as if the season has changed its mind, offering a few more days of grace. Indian summer is time borrowed, a pause in the progression toward cold, and perhaps that's why it feels so precious. Because it's unexpected, because we know it won't last, because it's a reminder to notice and appreciate beauty whenever it appears, even if, especially if it's fleeting. Tornadoes are fascinating and terrifying in equal measure. They form from severe thunderstorms when wind conditions create rotation in the storm system, typically when winds at different altitudes blow at different speeds or directions, creating a spinning horizontal tube of air. If rising air in the thunderstorm tilts this rotating tube toward vertical, a tornado can develop. The rotating column extends downward from the cloud base, and if it touches the ground, it becomes a tornado. Wind speeds inside tornadoes can exceed 300 miles per hour in the most violent ones, making them the most intense winds on the planet. The enhanced Fujita scale rates tornadoes from EF0 to EF5 based on damage, with EF5 tornadoes capable of completely obliterating well-built homes. Yet despite their power, tornadoes are typically quite narrow, often less than a quarter-mile wide, and they usually last only a few minutes. They're hyperlocal catastrophes, extremely violent but spatially limited. There's something almost surreal about tornado damage. One house completely destroyed, the one next door untouched, as if the tornado made deliberate choices about what to spare and what to demolish. Of course, it's just chance, just the specific path the vortex happened to take, but the randomness can make it feel personal, arbitrary, like fate rather than physics. The coldest layer of Earth's atmosphere isn't at the bottom. It's actually near the top of the mesosphere, roughly 50 miles up, where temperatures can drop to negative 130 degrees Fahrenheit or colder. This seems counterintuitive because we know that climbing a mountain gets you into colder air, so we expect temperature to keep dropping with altitude. And it does at first. The troposphere, where weather happens, gets colder as you go up. But then something changes. In the stratosphere, temperature actually increases with altitude because of ozone-absorbing ultraviolet radiation. Then in the mesosphere it gets cold again, extremely cold. This is because the air is so thin that there's very little to absorb and retain energy. It's a strange, in-between place, this mesosphere. Too high for weather, too low for space, cold beyond anything we experience at the surface. It's also where meteors burn up, where noctilucent clouds sometimes form, a frontier region that's hard to study because it's too high for balloons and too low for satellites to orbit. The mesosphere is a reminder that the atmosphere has layers, each with its own character, its own temperature profile, its own unique conditions. Wind chill isn't an actual temperature. It's a measure of how cold it feels when you factor in wind. On a still day, your body warms a thin layer of air right next to your skin, and that layer provides some insulation. But when wind blows, it strips away that warm layer, replacing it with colder air, forcing your body to work harder to warm the new air, making it feel colder than the actual air temperature. The wind chill factor attempts to quantify this effect, translating wind speed and actual temperature into an feels like temperature. So when the weather person says it's 20 degrees but feels like 5 with the wind chill, they're describing the increased rate of heat loss your body experiences. Wind chill can make the difference between uncomfortable and dangerous, between needing a heavier coat and risking frostbite. But wind chill only affects living things and objects that generate heat. It doesn't actually make the air colder or freeze things faster than the actual temperature would. A glass of water outside in 20-degree weather won't freeze any faster because of wind chill. It only freezes when the temperature is actually below freezing. Wind chill is perception made measurable, the subjective experience of cold given a number, a reminder that weather isn't just what happens in the air, it's what happens to us in our bodies, in our experience. Droughts are among the slowest of natural disasters, creeping up so gradually that they're often not recognized until they're severe. Unlike hurricanes or tornadoes, which announce themselves dramatically, droughts are defined by absence. The absence of rain, the absence of expected moisture. A drought begins when precipitation falls below normal levels for an extended period, but extended can mean months or years. Soil moisture depletes. Reservoirs shrink, rivers slow, vegetation withers, and all of this happens incrementally day by day, making it easy to underestimate until the situation becomes critical. Droughts remind us that weather isn't just about events, it's about patterns over time, about the accumulation of ordinary days that don't include rain. And while droughts are challenging, ecosystems have adapted to them. Many plants have evolved to withstand long dry periods, entering dormancy, reducing their water needs, waiting patiently for rain's return. When the drought finally breaks, there's often an explosion of growth. Everything that was waiting suddenly activated, as if the landscape was holding its breath and can finally exhale. Droughts are tests of endurance, reminders that life is resilient, that waiting is sometimes the only available strategy, and that rain, when it finally comes, is always worth the wait. Clouds can exist in supercooled states, meaning they're composed of water droplets that are below freezing temperature, but haven't actually frozen yet. This happens because pure water can remain liquid well below 32 degrees Fahrenheit if there's nothing for ice crystals to form around. No dust, no irregularities, no nucleation sites. These supercooled droplets are unstable, though. If an aircraft flies through a cloud of supercooled water, the droplets instantly freeze upon contact with the plane's surface, creating icing, a serious hazard that can affect flight controls and engines. Similarly, freezing rain occurs when supercooled raindrops fall through the air and then freeze instantly upon hitting surfaces at ground level, coating everything in smooth, clear ice. Supercooled water is potential energy, a phase of matter waiting for the right trigger to transform. And when that transformation happens, it happens instantly, liquid to solid in a fraction of a second, water finding its crystalline form all at once. It's a reminder that temperature isn't the only factor determining state of matter. Conditions, circumstances, the presence or absence of certain materials all play roles, creating possibilities for water to exist in unexpected states, for weather to surprise us with phenomena that seem to violate the rules until you understand the underlying physics. The dew point is a temperature threshold with real implications for comfort and health. It's the temperature at which air becomes saturated with water vapor and condensation begins. When the dew point is high, say, above 65 degrees Fahrenheit, the air feels sticky and oppressive because your sweat doesn't evaporate efficiently. Evaporation is how your body cools itself. But when the air is already holding lots of moisture, there's less capacity for more water vapor, so your sweat just sits on your skin, making you feel clammy and uncomfortable. When the dew point is low, below 50 degrees or so, the air feels crisp and dry, and your body's cooling mechanism works efficiently. Meteorologists often say that the dew point is a better measure of mugginess than humidity percentage, because it's an absolute measure rather than a relative one. 2 days might both have 70% humidity, but if one has a dew point of 45 and the other has a dew point of 70, they'll feel completely different. The latter will be nearly unbearable, while the former might feel quite pleasant. Dew point connects the abstract numbers of weather reports to the lived experience of being outside, translating atmospheric conditions into sensations your body immediately recognizes: comfort or discomfort, ease or struggle. Glaciers are essentially rivers of ice, flowing slowly downhill under their own weight, carving valleys and carrying rocks, shaping landscapes over millennia. They form in places where snow accumulation exceeds melting, mostly high mountains and polar regions. The snow compresses over decades and centuries, turning into firn and eventually into glacial ice. This ice is so dense, so compacted, that it appears blue. This happens because as light penetrates the ice, the long wavelength colors, reds and yellows, are absorbed, while blue light is scattered back out. The deeper and more compressed the ice, the more intensely blue it appears. Glaciers contain air bubbles from ancient atmospheres, trapped when the snow fell, preserved for thousands or even hundreds of thousands of years. Scientists drill ice cores from glaciers to study past climates, analyzing the chemistry of these bubbles to understand what Earth's atmosphere was like long before humans were around to measure it. Glaciers are libraries, archives, records written in ice, each layer a page from history. And they're also vulnerable. Many of the world's glaciers are retreating, melting faster than they are being replenished, responding to warming temperatures, their retreat itself becoming a record of climate change. The jet stream we mentioned earlier can split into branches, creating what meteorologists call a split flow pattern. When this happens, weather becomes complex and sometimes unpredictable because different parts of a region are influenced by different branches of the jet stream, pulling weather patterns in different directions. Sometimes the jet stream forms large loops called Rossby waves, named after the Swedish meteorologist Carl Gustaf Rossby. These waves can become amplified, meaning the loops get bigger, causing the jet stream to dip far south or arch far north. When this happens, unusual weather results: cold air penetrating deep into regions that are normally mild, or warm air pushing into high latitudes. These patterns can persist for days or weeks, creating extended periods of unusual weather. It's a reminder that the jet stream isn't a simple straight current but a complex, dynamic phenomenon, responsive to temperature differences, ocean currents, seasonal changes, and even events like volcanic eruptions or El Niño. The jet stream is the atmosphere's main highway for weather systems, and like any highway, it experiences traffic patterns, sometimes smooth flow, sometimes congestion, sometimes detours that reroute everything. Rain has a maximum falling speed, which might seem strange until you consider the physics. As a raindrop falls, it accelerates due to gravity, but it also experiences air resistance that increases with speed. Eventually, the raindrop reaches a speed where gravity's pull and air resistance balance out, and it stops accelerating. This is called terminal velocity. For typical raindrops, terminal velocity is around 20 miles per hour for small drops and up to about 20 miles per hour for larger ones. This is why rain doesn't hurt when it hits you, even though it's falling from clouds thousands of feet up. If raindrops were falling in a vacuum, they'd be moving at several hundred miles per hour by the time they reached the ground, fast enough to cause injury. But air resistance saves us, limiting how fast rain can fall, ensuring that precipitation is gentle rather than dangerous. It's one of those fortunate coincidences of physics, or perhaps not a coincidence at all, but simply the way the system works, air and water and gravity interacting in ways that happen to create conditions compatible with life. Rain is aggressive enough to water the earth, but gentle enough not to harm what's growing there. A perfect balance maintained by nothing more than air resistance and the properties of water droplets. The Coriolis effect, which we touched on earlier, is responsible for much of the large-scale structure of weather patterns. It's a consequence of Earth's rotation. Because Earth spins, objects moving across its surface appear to curve relative to the ground. In the northern hemisphere, moving objects curve to the right, in the southern hemisphere to the left. This effect is negligible for small-scale movements but significant for large-scale atmospheric flows. It's why high and low-pressure systems rotate, why hurricanes spin, why ocean currents curve across basins. At the equator, the Coriolis effect is zero. There's no deflection. This is partly why hurricanes don't form right at the equator. They need the Coriolis effect to get their rotation started. The Coriolis effect is invisible, intangible, but its influence is everywhere in weather and climate. It's a reminder that we live on a rotating sphere hurtling through space, and that rotation has consequences, shaping winds and currents, creating the swirls and spirals we see in satellite imagery, imposing order on what might otherwise be chaotic airflow. The Coriolis effect is planetary motion made manifest in weather, a connection between Earth's spin and the movement of air, a link between astronomy and meteorology. El Niño and La Niña are climate patterns that occur in the Pacific Ocean, involving changes in sea surface temperatures and atmospheric pressure. During El Niño, the eastern Pacific becomes unusually warm, which affects weather across the globe, wetter conditions in some areas, droughts in others, warmer winters in some regions, cooler in others. La Niña is essentially the opposite, with cooler than normal sea surface temperatures in the eastern Pacific, and it also influences global weather, but in different ways. These patterns typically last 9 to 12 months, sometimes longer, and they recycle every 2 to 7 years, though not on a perfectly regular schedule. What's remarkable is that a temperature change in one part of one ocean can influence weather patterns across the entire planet. Droughts in Australia, floods in South America, mild winters in Canada, more hurricanes in the Atlantic. It's all connected, all part of a global system where changes in one region propagate outward, affecting conditions thousands of miles away. El Niño and La Niña are proof that Earth's climate isn't a collection of isolated local systems, but a single integrated system, responsive and interconnected, where distant events have local consequences, where nothing happens in isolation. You're still here, and that's wonderful. Take a moment to notice how you're feeling. Perhaps your eyelids are growing heavy. Perhaps your mind is drifting between wakefulness and sleep, and that's perfectly fine. This is what this space is for, not to demand your attention but to accompany you gently into rest. The weather outside your window continues its eternal work, indifferent to whether you're awake to witness it, and that's comforting in its way. You don't have to stay conscious. You don't have to remember any of this. Let the words flow over you like water, like wind, present if you want them, distant if you don't. Everything is proceeding exactly as it should. The ozone layer, located in the stratosphere roughly 10 to 30 miles above Earth's surface, absorbs most of the sun's harmful ultraviolet radiation. Without it, life on land as we know it would be impossible. UV radiation is damaging to DNA and can cause mutations and cancer. Ozone is made of 3 oxygen atoms bonded together, and it's created when UV light splits ordinary oxygen molecules, freeing atoms that then bond with other oxygen molecules to form ozone. It's also broken down by UV light, so there's a constant cycle of creation and destruction. In the 1980s, scientists discovered that human-made chemicals called chlorofluorocarbons, CFCs, were depleting the ozone layer, creating a hole, actually a thinning over Antarctica. The world responded with the Montreal Protocol, an international agreement to phase out CFCs, and remarkably it worked. The ozone layer is now recovering, expected to return to 1980 levels by mid-century. It's one of the great environmental success stories, proof that global cooperation and action can reverse damage, that when humans recognize a problem and work together, solutions are possible. The ozone layer is invisible, taken for granted but essential, a shield of gas protecting the surface, allowing complex life to thrive in sunlight that would otherwise be sterilizing. Atmospheric pressure, the weight of all the air above you, is constantly changing, and your body responds to these changes, though usually unconsciously. Standard atmospheric pressure at sea level is 14.7 pounds per square inch, which means there are about 2,000 pounds of atmospheric pressure pressing on your body at any given moment. You don't feel crushed because your body's internal pressure balances it out. But when atmospheric pressure changes quickly, such as before a storm when pressure drops, some people feel it. Headaches, joint pain, changes in mood. Weather sensitivity is real, though not everyone experiences it. What's interesting is that many animals are much more sensitive to pressure changes than humans. Birds and insects change their behavior before storms, responding to pressure drops that warn of incoming weather. Fish move to different depths. Even cows reportedly lie down before rain, though the science on that is less clear. Pressure changes are invisible signals, information encoded in the weight of air, and some creatures can read these signals, predicting weather with senses we've largely lost or never had, reminding us that there are ways of knowing the world that don't require technology or instruments, just sensitivity to subtle changes in the environment. Clouds can produce optical phenomena beyond rainbows, halos, sun dogs, light pillars, and more. These occur when light interacts with ice crystals in high-altitude clouds, refracting and reflecting in specific ways depending on the crystal shape and orientation. A halo is a ring of light around the sun or moon, created by light refracting through hexagonal ice crystals. Sun dogs are bright spots that appear on either side of the sun, also caused by ice crystal refraction. Light pillars are vertical columns of light extending above or below a light source, caused by light reflecting off flat ice crystals that are fluttering down through the atmosphere. These optical effects are geometry made visible, crystalline structure translating into arcs and spots and pillars of light. They're more common than you might think, especially in winter or at high latitudes, but they require you to look, to notice the sky, to pay attention to the quality of light. Most people walk through their days without seeing these phenomena, even when they're present, because they're not looking up, not watching for subtle variations in ordinary light. But if you do look, if you train yourself to notice, the sky reveals itself as endlessly creative, constantly painting with light and ice and air. The concept of a normal temperature is actually a statistical average over a long period, usually 30 years. When meteorologists say today's high was above normal, they mean above the average high temperature for this date based on 3 decades of data. But climate changes, and so these normals are updated every decade to reflect current conditions. This means that normal is a moving target, shifting gradually as the climate warms or cools, as weather patterns change. It also means that extreme weather isn't defined by absolute values, but by how much a particular event deviates from expected patterns. A heat wave in one region might be pleasant weather in another. A cold snap in Florida is different from a cold snap in Minnesota. Context matters, history matters. And as climate continues to change, yesterday's extreme becomes today's normal, which is both a measurement challenge and a communication challenge. How do we talk about unusual weather when the baseline keeps shifting? The answer, perhaps, is to remember that climate is always changing, has always been changing, though typically much more slowly than what we're experiencing now. Our current normals will not be our future normals, and the weather our grandchildren experience will likely be different from what we've known. Monsoons are not just heavy rains, they're seasonal wind pattern reversals that affect large regions, most famously in South Asia and parts of Africa and the Americas. In summer, land heats up faster than the ocean, creating low pressure over the continent. Moist ocean air flows toward the low pressure, bringing heavy rains, the wet monsoon. In winter, the pattern reverses. The land cools, high pressure develops, and dry air flows from land to ocean, the dry monsoon. These seasonal shifts are predictable, life-shaping events. Agriculture depends on monsoon rains. Cultures have organized around monsoon patterns for thousands of years. The word monsoon comes from the Arabic mawsim, meaning season, because these winds and their associated weather are so regular, so defining that they essentially are the seasons in affected regions. A late monsoon or weak monsoon can spell disaster, drought, failed crops, water shortages. An unusually strong monsoon can bring flooding, landslides, destruction. Monsoons are demonstrations of the intimate relationship between land and sea, between differential heating and atmospheric circulation, but they're also deeply human stories of anticipation and preparation, of celebration when the rains arrive, of anxiety when they don't, of civilizations shaped by seasonal rhythms of wet and dry, abundance and scarcity. Cumulus clouds are often described as fair weather clouds, but they're also the nurseries for thunderstorms. A cumulus cloud is a sign of rising warm air. If conditions are right, enough moisture, enough instability in the atmosphere, sufficient temperature difference between surface and upper air, that cumulus cloud can grow upward, piling higher and higher, transforming from a small puffy cloud into a towering cumulonimbus, the thunderstorm cloud. These can reach heights of 50,000 feet or more, with their tops spreading out into an anvil shape as they hit the tropopause, the boundary between the troposphere and stratosphere, unable to rise further. Inside these enormous clouds, updrafts and downdrafts create intense turbulence, hail forms, lightning generates, and eventually the whole system becomes unstable, producing torrential rain, sometimes tornadoes, sometimes damaging winds. But it all starts with a small cumulus cloud, a puff of white against blue sky, innocuous, almost cheerful. Weather is transformation, potential realized or dissipated, energy building until it must be released. That small cloud could vanish in 10 minutes, or it could grow into a storm system spanning counties, all depending on the specific conditions at that moment in that place. Frost forms patterns because ice crystals grow along specific axes determined by molecular structure. Water molecules bond in hexagonal arrangements, and as frost forms, the crystals extend along these preferred directions, creating the branching, feather-like patterns we see on cold windows. Each branch grows at 60-degree angles from the main stem, following crystalline rules, and smaller branches grow from the larger ones, all maintaining the underlying hexagonal geometry. What's beautiful is that these patterns emerge from simple rules followed countless times, each water molecule attaching to the growing crystal in the configuration that's lowest energy, that's most stable, and the aggregate result is intricacy and apparent design. Frost patterns are emergent complexity, order arising from simple interactions repeated at molecular scale. They're also temporary art, existing for the hours between night's cold and morning's warmth, vanishing as soon as temperatures rise, leaving only clear glass where moments before there were forests and feathers of ice. Frost is impermanence made visible, beauty that doesn't try to last, that accepts its brief existence and disappears without complaint, offering itself fully in the moment it has. The greenhouse effect is essential for life on Earth, though it's often discussed only in negative terms. Without any greenhouse effect, Earth's average temperature would be around 0 degrees Fahrenheit, far too cold for liquid water or life as we know it. Greenhouse gases, water vapor, carbon dioxide, methane, and others, trap heat in the atmosphere. They allow visible light from the sun to reach the surface but absorb infrared radiation that Earth emits, preventing all of it from escaping back into space. This trapped energy warms the atmosphere, creating temperatures that can support life. The problem isn't the greenhouse effect itself, but the enhancement of it through increased greenhouse gas concentrations, primarily from burning fossil fuels. More greenhouse gases mean more heat trapped, meaning higher temperatures, meaning climate change. But the underlying mechanism, gases that trap heat, is not inherently bad. It's natural, necessary, the reason Earth is habitable rather than frozen. The issue is balance, proportion, the difference between a greenhouse that warms gently and one that overheats. Earth's climate is a system with optimal operating conditions, and we're pushing it outside those conditions, not because the mechanisms are flawed, but because we're amplifying them beyond historical levels. Evaporation is a cooling process, which is why sweating cools you down and why wet surfaces feel cold. When water evaporates, molecules with higher kinetic energy, the faster moving, hotter molecules escape from the liquid surface into the air. This leaves behind molecules with lower average energy, meaning the remaining liquid is cooler. This is also why evaporative coolers work in dry climates. They blow air through water-saturated pads, evaporating the water and cooling the air. It's an elegant system, using a phase change to transfer heat, and it's the same principle your body uses for thermoregulation. When you're hot, you sweat, and as the sweat evaporates, it pulls heat from your skin. Humidity interferes with this process, which is why high humidity makes heat feel worse. Your sweat can't evaporate efficiently, so your cooling system struggles. But in dry conditions, evaporation is rapid and cooling is effective, which is why deserts can be bearable at 100 degrees while humid climates are miserable at 85. Evaporation is molecular escape, a phase transition, and also a heat transfer mechanism, physics working to distribute energy, to achieve equilibrium, indifferent to human comfort but shaping our experience nonetheless. Barometric pressure, atmospheric pressure measured by a barometer, is a useful tool for weather prediction. Falling pressure generally indicates worsening weather, clouds, precipitation, storms moving in. Rising pressure suggests improving conditions, clearing skies, drier weather. This works because low-pressure systems are associated with rising air, which cools and condenses, forming clouds and precipitation, while high-pressure systems involve sinking air, which warms and dries out, creating clear conditions. Early barometers were just tubes of mercury, open at the bottom and closed at the top, with the mercury rising or falling as atmospheric pressure changed. Now most barometers are aneroid, using a flexible metal chamber that expands or contracts with pressure changes. But the principle is the same. Atmospheric pressure is information, a signal about what's happening in the weather system. Sailors and farmers and anyone who spent time outside learned to read barometers, to interpret the subtle messages of pressure change. It's a conversation between instruments and weather, measurements translating atmospheric conditions into predictions, giving us a window into the future. Not perfect, not certain, but better than nothing. Better than simply waiting to see what happens. Snow is an excellent insulator, which is why igloos work and why plants buried under snow often survive harsh winters. Snow is mostly air. The spaces between ice crystals trap air, and air is a poor conductor of heat. This means that snow prevents heat from escaping. Animals burrow into snow for warmth. Plants are protected from the worst temperature extremes by their snow cover. Even a few inches of snow can create a significantly warmer microenvironment at ground level compared to the exposed air above. This insulating property also means that snow-covered ice on lakes melts more slowly than exposed ice. The snow acts as a barrier, preventing warm air from directly reaching the ice surface. Snow's insulating quality is why winter camping in snow can actually be warmer than camping in cold, clear conditions without snow. You can dig a snow cave, and the interior will be noticeably warmer than outside, heated just by your body heat and insulated by the snow walls. It's counterintuitive. Snow seems cold, and it is, but it's also protective, a frozen blanket, evidence that materials have properties beyond what they immediately appear to have. That apparent coldness can actually provide warmth under the right circumstances. The stratosphere is where the ozone layer resides, but it's also remarkably stable compared to the troposphere below. In the troposphere, temperature decreases with altitude and weather is constantly changing. But in the stratosphere, temperature actually increases with altitude because ozone absorbs UV radiation, converting it to heat. This temperature inversion, warm air over cool air, creates stability. Warm air doesn't want to rise if there's even warmer air above it, so vertical mixing is limited. This is why the stratosphere is calm, clear, nearly weather-free. Commercial jets often cruise in the lower stratosphere because it's smooth, stable, and has less air resistance than lower altitudes. It's also why pollutants that reach the stratosphere can stay there for years. There's no rain to wash them out, limited mixing to disperse them. The stratosphere is a different realm, governed by different rules, a layer of atmosphere where weather as we know it doesn't happen, where everything is calmer, thinner, more stable. It's a reminder that the atmosphere isn't a uniform thing but a stack of distinct layers, each with its own characteristics, its own behavior, its own role in the larger system. Clouds don't just float, they're actively maintained by updrafts. A cloud exists because air is rising, cooling as it ascends, reaching its dew point and condensing into droplets. If the updraft stops, the cloud begins to evaporate. This is why clouds often have sharp, defined edges. Inside the cloud, air is saturated and droplets persist. Outside the cloud, air is drier and droplets evaporate. Clouds are processes sustained by energy, not static objects but dynamic systems in temporary equilibrium. When you watch a time-lapse of clouds, you see them boiling and churning, growing and shrinking, because they're responding to atmospheric conditions that are constantly changing. Some clouds last minutes, others last hours, but all of them exist only as long as the conditions that created them persist. Clouds are embodied change, visible evidence of atmosphere in motion, of energy flowing from one form to another, of water cycling between liquid and vapor, between visible and invisible. To understand clouds is to understand that weather is process, not state, that what looks solid is actually flowing, that what seems permanent is actually temporary, that everything is in flux always. Rainbows appear as arcs because of geometry. The angle at which light refracts and reflects inside water droplets is fixed at about 42 degrees. Your eyes can only see rainbow light coming from droplets at that specific angle relative to the sun, which traces out a circle in the sky. You see only the upper half of that circle because the ground blocks the lower half, creating an arc. But if you're in an airplane or on a mountaintop looking down on rain, you can sometimes see a full circle rainbow, the complete geometric form normally hidden by the horizon. These circular rainbows are proof that the arc we usually see is a cross-section of something whole, a partial view of a complete phenomenon. Rainbows demonstrate that our perspective shapes what we see, not in some metaphorical sense, but literally, physically. Move your position and the rainbow moves. You can never show someone else exactly the rainbow you're seeing because each observer is at the center of their own optical geometry, creating their own unique rainbow from their own unique perspective. It's a lovely metaphor, really, that beauty is partially subjective, determined by where you stand, by what angle you approach from, by the specific conditions of your viewing position. Weather satellites have transformed meteorology, giving us a perspective on weather systems that was impossible before the space age. Satellites orbit Earth, looking down, taking images in various wavelengths of light, measuring temperature, moisture, wind patterns. They let us see hurricanes forming over the ocean, watch storm systems move across continents, track clouds in real time. Before satellites, weather forecasts were based on reports from scattered observation stations. Weather ships, weather balloons, airport sensors, and meteorologists would draw maps by hand, connecting data points, inferring what was happening between stations. Now we have continuous global coverage, images updating every few minutes, data flowing constantly. Weather forecasting has improved dramatically because we can see the weather, not just infer it. We can track a storm's actual movement rather than guessing where it might go. Satellites are our eyes in space, our way of comprehending weather as a planetary system rather than a collection of local events. They've made the invisible visible, turned guesswork into science, and saved countless lives by improving warning times for severe weather. And they've given us beauty, too. Those images of Earth from space, swirled with clouds, blue and white and beautiful. A reminder that we live on a living planet, dynamic and complex and utterly extraordinary. Temperature inversions occur when a layer of warm air sits atop cooler air near the surface, which is the opposite of the normal temperature profile. Inversions are stable. Cool air doesn't rise through warm air because it's denser, so they trap air at the surface. Pollutants and moisture can't easily disperse, leading to smog, fog, or hazy conditions. Inversions often happen on clear, calm nights when the ground radiates heat away, and the air right above it cools rapidly while the air higher up remains warmer. They also form in valleys where cold air drains downhill and pools at the bottom, trapped by surrounding terrain. Temperature inversions are why valleys often have worse air quality than nearby hills, why some cities have chronic smog problems, why certain areas experience persistent fog. They're also why frost forms even when the official temperature at 5 feet above the ground is above freezing. At ground level, inside the inversion, it's colder. Inversions are atmospheric lids, seals that keep everything pressed down, waiting to be broken by sunrise or wind or some change in conditions that disrupts the stable layering and allows normal mixing to resume. Lightning doesn't always strike the ground. Much lightning occurs entirely within clouds, jumping between regions of positive and negative charge. This is called intra-cloud lightning, and it's actually more common than cloud-to-ground strikes. You see it as the cloud lighting up from within, flickering, illuminating itself, as if the storm is thinking, processing, working through electrical imbalances internally. Sheet lightning is intra-cloud lightning that's far enough away that you don't see the distinct bolt, just the general brightening of the cloud or horizon. Lightning is the atmosphere's way of balancing charge. Storms separate electrical charge through complex interactions between ice crystals, water droplets, and updrafts, creating regions of strong positive and negative charge. Eventually, the voltage difference becomes so great that air, normally an insulator, breaks down and becomes conductive, allowing current to flow, equalizing the charge. The channel heats to extreme temperatures, glows brilliantly, and generates thunder. Lightning is violence and balance, destruction and restoration, nature's reset button pressed thousands of times during a single storm, the atmosphere equalizing itself, returning to electrical neutrality, only to immediately begin building charge separation again. Fog often forms in valleys at night because cold air is denser than warm air and flows downhill, settling in low areas. As the air cools, it reaches its dew point and moisture condenses, creating fog that pools like an invisible liquid, filling valleys, covering low-lying areas while hilltops remain clear. If you've ever driven down a hill and suddenly entered fog, then climbed another hill and emerged into clear air, you've experienced this layering, fog behaving like a lake of moisture, with definite depth and a surface you can move through. Radiation fog forms this way, created by radiative cooling on clear, calm nights. Advection fog is different. It forms when warm, moist air moves over a cold surface, cooling to its dew point. This happens near coastlines when warm air moves over cold ocean water, creating the persistent fog characteristic of places like San Francisco. Fog is atmosphere touching ground, cloud descending, visibility reduced to intimate distances. It alters sound, softens light, makes the world mysterious and close. And then it lifts, usually as the sun rises and warms the air, increasing its capacity to hold water vapor, evaporating the fog back into invisible vapor, returning visibility, opening the world back up to distances. Let yourself rest deeply now if you need to. Your breathing has probably slowed. Your body has settled. The world continues outside, clouds drifting, winds moving, the patient turning of weather patterns across the planet, and you're safe here, learning about it all, letting the information arrive without effort. There's nothing you need to do with these facts, no test to pass, no requirement to remember. They're here to accompany you, to fill the space gently, to give your mind something soft to hold on to as you drift towards sleep. You're doing perfectly. Everything is exactly as it should be. Rest now. The polar vortex is a large area of low pressure and cold air surrounding Earth's poles. It exists year-round, though it's strongest in winter. The vortex is normally contained at high latitudes by the jet stream, but sometimes it weakens or becomes distorted, allowing frigid polar air to spill southward, bringing extreme cold to regions that don't usually experience it. When this happens, news reports talk about the polar vortex descending, as if it's an invading entity, but really it's just cold air escaping its usual containment, flowing where pressure gradients and wind patterns allow. These cold outbreaks can be severe at temperatures dropping dramatically, setting records, creating dangerous conditions for people unprepared for that level of cold. But the polar vortex itself is a natural feature, part of the atmospheric circulation, not a new phenomenon created by climate change. What may be changing is how often and how far the vortex becomes disrupted, potentially related to warming in the Arctic affecting the jet stream. Weather patterns are interconnected in ways we're still understanding, where changes in one region propagate outward, creating effects that seem distant and unrelated but are actually connected through atmospheric dynamics. Precipitation doesn't only happen as rain or snow. There's also freezing rain, which is different from sleet. Freezing rain falls as liquid water but freezes instantly upon contact with surfaces that are below freezing, creating a coating of glaze ice. Sleet, on the other hand, is rain that freezes into ice pellets while still in the air, before hitting the ground. Both are hazardous but in different ways. Freezing rain creates extremely slippery surfaces and can coat power lines and tree branches, adding weight until they snap. Sleet bounces and accumulates more like snow. Then there's graupel, sometimes called soft hail, which forms when supercooled water droplets freeze onto falling snowflakes, creating small, soft, opaque pellets of ice. Graupel is common in winter storms but often goes unnoticed because it resembles small hail or dense snow. The variety of precipitation types is evidence of how many different atmospheric conditions exist, how temperature, humidity, and altitude interact to create dozens of variations on the theme of frozen or liquid water falling from the sky. Each type has its own formation process, its own requirements, its own character and effects. The coldest temperature ever reliably recorded on Earth's surface was at the Soviet Vostok station in Antarctica, -128.6 degrees Fahrenheit in July 1983. More recently, satellite data has recorded even colder temperatures in Antarctic valleys, down to -144 degrees Fahrenheit. But these are surface temperatures of snow and ice, not air temperatures. At those temperatures, exposed skin would freeze in seconds. Metal becomes brittle. Ordinary materials behave strangely. These extreme cold temperatures exist because Antarctica is high altitude, covered in reflective ice and snow, and experiences months of darkness during winter. Heat radiates away into space, and there's no sunlight to provide warmth. The continent becomes a vast freezer, accumulating cold, descending to temperatures that seem more appropriate to outer space than to a planetary surface. And yet life exists even there. Microorganisms in the soil, bacteria in lakes beneath the ice, all adapted to conditions that seem utterly hostile to life. Cold is relative, survivable, just another environmental variable that life has found ways to accommodate. Antarctica is a reminder that Earth contains extremes, that the range of conditions on this planet is vast, that what seems uninhabitable to us is home to something, somewhere, adapted across evolutionary time to conditions we find unimaginable. Wind erosion is a powerful geological force, especially in deserts where vegetation is sparse and can't hold soil in place. Wind picks up particles and carries them, sometimes for hundreds of miles. The smallest particles, silt and clay, can be lifted high into the atmosphere and carried across continents or even oceans. Larger particles, sand, are transported in a process called saltation, where they bounce along the ground, kicked up by wind, falling, then bouncing up again. Over time, wind-blown sand abrades rock, sculpting formations, polishing surfaces, creating ventifacts, rocks shaped and faceted by wind-driven particles. Wind erosion is slower than water erosion in most environments, but in deserts, it's dominant, the primary sculptor. Sand dunes migrate across landscapes, burying some areas, exposing others, creating ecosystems that are constantly shifting. Wind is patient violence, wearing down mountains grain by grain, redistributing entire deserts particle by particle, shaping the planet's surface in ways that are invisible moment to moment but dramatic over years and centuries. The wind that you barely notice, that just ruffles your hair, is the same wind that, given time and the right conditions, can level mountains and build dunes miles long. Humidity affects not just comfort but also how efficiently the human body can cool itself. At 100% humidity, the air is completely saturated. It can't hold any more water vapor. Your sweat can't evaporate because there's nowhere for the moisture to go, so your primary cooling mechanism fails. This is why high humidity makes heat dangerous. It's not just that it feels uncomfortable. It's that your body can't regulate its temperature effectively. Heat index calculations attempt to combine temperature and humidity into a single number that represents how hot it actually feels and how dangerous the conditions are. A temperature of 95 degrees with 50% humidity might have a heat index of 107, meaning it feels like 107 degrees and poses serious heat stress risks. Conversely, low humidity helps your body cool efficiently, which is why desert heat is often more tolerable than humid heat despite sometimes higher actual temperatures. Humidity is invisible but consequential, a variable that determines whether hot weather is merely uncomfortable or genuinely dangerous. Weather isn't just about temperature. It's about the whole package of atmospheric conditions interacting with human physiology, creating experiences and risks that can't be captured by a single number. Atmospheric rivers are long, narrow bands of concentrated moisture in the atmosphere, typically stretching thousands of miles and carrying enormous amounts of water vapor. When an atmospheric river makes landfall, especially on mountainous coasts, it can produce extreme rainfall, sometimes leading to flooding and landslides. The term was coined relatively recently, but the phenomenon is not new. These are the storm systems that bring heavy rain to the west coast of North America, that cause flooding events in California and the Pacific Northwest, that deliver much of the region's annual precipitation in just a few intense storms. An atmospheric river can carry more water than the flow of the Mississippi River, except the water is in vapor form, suspended in air, transported across oceans, waiting to condense and precipitate when conditions are right. They're essential for water supply in some regions. Without atmospheric rivers, reservoirs wouldn't fill. Water shortages would be even more severe. But they're also hazards, capable of overwhelming drainage systems, triggering mudslides, causing damage and disruption. Atmospheric rivers are another demonstration that weather happens on scales both large and small. That seemingly local rainfall is actually the expression of enormous transport systems moving moisture around the planet. Part of the global hydrological cycle, operating at continental scales. Climate zones are regions of Earth characterized by similar weather patterns over long periods. The most familiar system is the Köppen climate classification, which divides the world into categories based on temperature and precipitation: tropical, dry, temperate, continental, and polar, with further subdivisions within each. These zones exist because of Earth's spherical shape and axial tilt, which create different solar radiation levels at different latitudes, which in turn drive atmospheric circulation patterns that distribute heat and moisture unequally. Tropical zones near the equator receive intense sunlight year-round and have warm temperatures with significant rainfall. Polar zones receive oblique sunlight and remain cold. Temperate zones experience distinct seasons as the angle of sunlight changes throughout the year. These broad patterns create the basis for ecosystems, agriculture, human settlement patterns. Climate shapes what can grow where, what kind of shelter is needed, how societies develop. And climate zones are shifting now, moving poleward as global temperatures rise, altering the conditions that have characterized regions for centuries, creating new challenges for agriculture and ecosystems adapted to historical climate patterns. Climate is fate in many ways, not deterministic, but influential, setting the parameters within which life organizes itself. Clouds can be seeded to encourage precipitation, though the effectiveness is debated. Cloud seeding involves dispersing substances like silver iodide into clouds. These particles act as nucleation sites, giving water vapor or supercooled droplets something to condense or freeze onto, potentially creating precipitation that wouldn't have occurred otherwise, or accelerating precipitation that would have occurred eventually. The technique has been used to enhance snowfall in mountains to improve water supply, to attempt to reduce hail damage, to try to clear fog from airports. But proving that cloud seeding actually worked, that rain fell because of the seeding rather than natural processes, is difficult. You can't know what would have happened without the seeding. The practice is controversial, with questions about effectiveness, cost, unintended consequences, and even legal issues about who owns water vapor, and whether one region has the right to extract precipitation that might otherwise have fallen elsewhere. Cloud seeding is humanity attempting to take control of weather, to manage precipitation, to exert influence over atmospheric processes. It's a small-scale intervention, and whether it represents the beginning of weather modification or just an expensive placebo is still being studied, still being argued about, still uncertain. The concept of wind chill doesn't apply to inanimate objects. Wind chill describes how cold it feels to living creatures based on heat loss, but a thermometer will read the same temperature regardless of wind speed. An object left outside in 20-degree weather with high wind will eventually cool to 20 degrees, not to the wind chill temperature. The wind speeds up the cooling process. It'll reach 20 degrees faster, but it won't get colder than the actual air temperature. This matters for practical reasons. Frozen pipes, for instance, depend on actual air temperature, not wind chill. But for living things, wind chill is absolutely relevant because it describes the rate of heat loss from warm bodies exposed to moving cold air. Your body generates heat, and wind removes it, and the faster you lose heat, the colder you feel and the greater the risk of hypothermia or frostbite. Wind chill is perception made measurable, biology made mathematical, the interface between environment and organism quantified. It's a number designed for living things, a translation of physical conditions into physiological effects, a reminder that weather isn't just atmospheric conditions, but the interaction between atmosphere and whatever exists within it, people, animals, plants, all responding to the same conditions in different ways. Desert climates have extreme temperature swings between day and night. This happens because dry air doesn't retain heat well. Without water vapor to trap outgoing infrared radiation, heat radiates away into space rapidly once the sun sets. During the day, the desert heats intensely because there's little moisture or cloud cover to block incoming solar radiation. But at night, that heat escapes, and temperatures can drop 40 or 50 degrees Fahrenheit, sometimes even reaching freezing. This diurnal temperature range, the difference between daytime high and nighttime low, is one of the defining characteristics of desert climates. It creates challenges for organisms, which must cope with extreme heat and cold within a single 24-hour cycle. Humans living in deserts traditionally built thick-walled structures that absorb heat during the day and release it slowly at night, moderating the indoor temperature swings. Desert plants and animals have evolved strategies, burrowing underground where temperature is more stable, being active only during certain hours, physiological adaptations that allow them to tolerate rapid temperature changes. Deserts demonstrate in extreme form what's true everywhere: that moisture mediates temperature, that water in the atmosphere is a buffer against extremes, that climate is as much about humidity as about latitude or sunlight. Snowfall is difficult to predict accurately because it depends on multiple factors that are hard to forecast precisely: temperature at the surface, temperature aloft, precipitation rate, and more. A change of just a few degrees can mean the difference between rain and snow, or between light flurries and a major accumulation. Forecasters often give snowfall predictions as ranges: 3 to 6 inches expected, acknowledging the uncertainty. And snow accumulation depends not just on how much falls but on what kind of snow. Wet, heavy snow compacts more than light, fluffy snow, so the same depth might represent very different amounts of precipitation. The water content of snow varies widely, with some snow containing 10 times as much water per inch as other snow. This is why meteorologists sometimes talk about snow-to-liquid ratios. How much liquid water would result from melting a given depth of snow? A typical ratio is 10:1, meaning 10 inches of snow equals 1 inch of liquid water, but it can range from 5:1 for wet snow to 30:1 for very dry, fluffy snow. Predicting snow is predicting a phase transition dependent on atmospheric conditions that themselves are uncertain, a cascade of variables where small changes propagate into large differences, making precision difficult and humility necessary. Auroras, the northern and southern lights, are technically weather, though not in the troposphere where ordinary weather happens. They're space weather occurring in the upper atmosphere, 60 to 200 miles up, where charged particles from the solar wind collide with atmospheric gases. These collisions excite atoms, causing them to emit light, green and red from oxygen, blue and purple from nitrogen. The solar wind is deflected by Earth's magnetic field, channeled toward the poles, which is why auroras are most commonly seen at high latitudes. During strong solar storms, when the sun releases bursts of charged particles in events called coronal mass ejections, auroras can be visible much farther from the poles than usual. Auroras are invisible forces made visible, magnetic fields and solar particles and atmospheric gases, interacting to create curtains of light that shimmer and dance across the sky. They're evidence that Earth is not isolated but constantly bathed in the solar wind, protected by its magnetic field, part of a larger system that includes the sun, the space between, the constant flow of particles and energy and magnetic influence. Auroras are beautiful accidents of physics, side effects of planetary protection, proof that the cosmos is active even in the apparent emptiness of space. Sublimation is when a substance transitions directly from solid to gas without passing through the liquid phase. Ice sublimates under certain conditions. This is why snow can disappear even when the temperature stays below freezing, especially in dry, windy conditions. The ice doesn't melt, it evaporates directly into water vapor. This is also why ice cubes in your freezer shrink over time even though they never melt, and why frozen foods can get freezer burn. The water in the food sublimates, leaving dry spots. Sublimation is more common than you might think, happening constantly at the surface of snow and ice, contributing to glacier mass loss, affecting the persistence of snowpack. Its phase transition taking a shortcut, skipping the middle state, demonstrating that matter's phases aren't always linear progressions, but can jump between states depending on temperature and pressure conditions. Sublimation is elegant in its efficiency, solid to gas directly, and it's a reminder that the water cycle includes more pathways than just the obvious ones we learn in elementary school. Water doesn't just evaporate from liquid, it can evaporate from solid, completing the journey from ice to vapor in a single quiet transformation. Heat lightning is a misnomer. There's no such thing as lightning caused by heat. What people call heat lightning is just regular lightning from a thunderstorm that's too far away for you to hear the thunder. You see the lightning illuminate the sky or the clouds, but the storm is so distant that the thunder dissipates before reaching you. Sound fades with distance faster than light does, So there's a range where you can still see lightning, but can no longer hear the associated thunder. Heat lightning often appears on summer evenings as flickers on the horizon, distant storms backlighting clouds. And because it's not accompanied by thunder or rain where you are, it seems like a different phenomenon. But it's just distance creating the illusion of difference. The storm is real, the lightning is real, the thunder is real. You're simply too far away to experience all of it. Heat lightning is a reminder that weather happens on scales larger than our immediate perception, that storms exist over the horizon, beyond our hearing, visible only as flashes in the distance, echoes of violence too remote to threaten us but close enough to see. Mountains create their own weather patterns. As air approaches a mountain, it's forced upward. As it rises, it cools, and if it cools below its dew point, moisture condenses and clouds form. This is why mountains often have clouds clinging to their peaks, and why mountains receive more precipitation than surrounding lowlands. The windward side of a mountain, the side facing the prevailing wind, gets heavy precipitation. But as air crosses the peak and descends the other side, it warms and dries out, creating a rain shadow, a region on the leeward side of the mountain that receives much less precipitation. This is why landscapes can change dramatically over short distances in mountainous areas, one side lush and green, the other arid. The Pacific Northwest of the United States demonstrates this beautifully. Coastal areas are temperate rainforests, drenched by moisture from the Pacific, while areas just east of the Cascade Mountains are semi-arid, the mountains having wrung out most of the moisture before the air reaches them. Mountains don't just experience weather, they shape it, force it, impose their will on air masses, creating climate zones that wouldn't exist on flat terrain. The water cycle, or hydrological cycle, is the continuous movement of water between ocean, atmosphere, and land. Water evaporates from the ocean, rises into the atmosphere, condenses into clouds, falls as precipitation onto land or ocean, flows in rivers back to the ocean, and the cycle continues. But it's not perfectly circular. Water can be stored at various stages for vastly different amounts of time. Water in the atmosphere stays there for about 9 days on average before precipitating. Water in rivers might take weeks or months to reach the ocean. Groundwater can remain underground for thousands of years. Water frozen in glaciers might stay frozen for tens of thousands of years. So the water cycle isn't a simple loop. It's a complex system with short-term and long-term storage, with multiple pathways and timeframes, with water entering and leaving various reservoirs at different rates. The water cycle is a process, a flow, a system that's always in motion even when parts of it seem static. And it's driven by energy from the sun, which evaporates water, and by gravity, which pulls it back down. The water cycle is one of Earth's fundamental systems, essential for climate, for life, for shaping the planet's surface through erosion and deposition. Contrails, condensation trails left by aircraft, are artificial clouds. They form when hot, humid exhaust from jet engines mixes with cold air at high altitude. The water vapor in the exhaust condenses and freezes instantly, creating a visible trail of ice crystals that can persist for minutes or hours, depending on atmospheric conditions. In dry air, contrails dissipate quickly. In humid air, they can linger and spread, forming cirrus-like clouds that cover significant areas of sky. There's ongoing research into whether contrails affect climate. They're essentially high-altitude clouds that trap outgoing infrared radiation, contributing to warming, though the effect is small compared to greenhouse gas emissions from burning fuel. Contrails are human marks on the sky, our activities made visible at altitude, scripting our paths across the atmosphere in lines of ice. They're accidental art, unintended consequences of aviation, temporary additions to the cloud inventory, proof that humans are now participants in atmospheric processes, not just observers, actively adding moisture and particles to altitudes that were pristine before the jet age. Ball lightning is one of weather's mysteries. Reports of glowing, spherical objects appearing during thunderstorms, lasting seconds, sometimes moving horizontally, sometimes passing through walls or windows, then vanishing or exploding. For years, ball lightning was dismissed as retinal afterimages from regular lightning or hallucinations, but enough credible reports exist that scientists now believe it's a real phenomenon, though the mechanism remains unclear. Theories involve plasma, microwave radiation, chemical reactions, or other exotic physics. Ball lightning is rare, unpredictable, difficult to study, and no one has successfully created it in a lab in a way that matches natural reports. It exists at the edge of scientific understanding, a reminder that despite all our instruments and knowledge, weather can still produce phenomena we don't fully understand, events rare enough that we haven't captured them adequately. Mysteries that persist because nature doesn't always cooperate with our desire to observe and measure. Ball lightning is wonder, enigma, the unknown persisting in a domain we thought we'd thoroughly catalogued. Take a deep breath if you'd like, or your breathing is perfect just as it is. Let your eyes rest. Let your jaw unclench if it's holding tension. The facts are here, gentle and steady, asking nothing of you. You can drift in and out of awareness, catching words and ideas as they float by, or you can release even that and simply exist in this moment, safe and still. The weather outside continues, rain falling or not falling, wind blowing or air still, clouds forming and dissolving, all of it happening without requiring anything from you. Rest. Listen. Let go. Everything is well. Trade winds are consistent easterly winds that blow near the equator, between roughly 30 degrees north and 30 degrees south latitude. They're called trade winds because they were essential for sailing ships engaged in trade routes. Reliable, predictable winds that could be counted on to fill sails and carry cargo across oceans. Trade winds are part of the Hadley cell circulation. Air rises at the equator, flows poleward at high altitude, descends around 30 degrees latitude, and flows back toward the equator at the surface. The Coriolis effect bends these surface winds westward, creating the easterly trade winds. They blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, converging at the equator in a region called the Intertropical Convergence Zone, where rising air creates clouds, rain, and thunderstorms. Trade winds are planetary scale patterns, atmospheric rivers of air, evidence of Earth's circulation systems organizing weather into predictable structures. They've shaped human history, exploration, colonization, commerce, all dependent on understanding and utilizing these reliable winds. The trade winds are still there, still blowing, still shaping climate and weather, even though we no longer depend on them for transportation. A temperature of 70 degrees Fahrenheit feels different in different seasons. In winter, after months of cold, 70 feels warm, almost balmy, prompting people to shed coats and venture outside. In summer, after weeks of heat, 70 feels cool, pleasant, a relief. This is partly psychological, context and expectation matter, but it's also physiological. Your body acclimatizes to prevailing temperatures, and what feels normal shifts based on what you've been experiencing. People who live in cold climates are comfortable at temperatures that would make tropical residents shiver, and vice versa. Acclimatization is real, affecting how blood vessels constrict or dilate, how efficiently you sweat, how your metabolism generates heat. Temperature isn't an absolute experience but a relative one, perceived in context, judged against recent history. A 70-degree day in March is wonderful. The same temperature in August is sweater weather. This relativity is part of why climate change is psychologically difficult to grasp. We're adapted to variability, to seasons, to fluctuations, and we interpret each temperature in context rather than as part of a long-term trend. Our bodies are designed for local adaptation, not global perspective. Clouds can be streets or cells, patterns that form depending on wind conditions. Cloud streets are long, parallel rows of cumulus clouds aligned with the wind direction, created by helical circulation patterns in the lower atmosphere. From above, they look like lanes on a highway, stretching for miles, evenly spaced, remarkably regular. Cloud cells are more common over the ocean, where cold air moves over warmer water, creating convection. The clouds form in roughly hexagonal patterns with clear areas between them, like a honeycomb, visible in satellite imagery as repeating geometric shapes covering vast areas. These patterns are self-organizing, the atmosphere finding efficient ways to transport heat, creating regularity from chaotic processes. Cloud streets and cloud cells are examples of emergent order, pattern arising from simple rules applied at large scale, evidence that the atmosphere isn't random chaos but structured, organized, following physical laws that produce beautiful, repeating forms. Looking at satellite images of these cloud patterns is like looking at art, except the artist is just physics, just temperature and moisture and wind interacting according to unchanging rules. Humidity is often misunderstood. Relative humidity is what's usually reported. It's the amount of moisture in the air relative to the maximum amount the air could hold at that temperature. This means relative humidity changes with temperature, even if the actual amount of water vapor stays constant. Cool air at night might have 90% relative humidity, and then in the afternoon when it's warmer, the relative humidity might drop to 40%, even though the amount of water vapor hasn't changed. That's because warm air can hold more moisture, so the same amount of water vapor represents a smaller percentage of the maximum capacity. Absolute humidity, on the other hand, is the actual amount of water vapor present, regardless of temperature. Dew point is another measure, the temperature to which air must be cooled for saturation to occur. Dew point is often a better indicator of comfort than relative humidity because it's an absolute measure. All of these are ways of describing moisture in the air, different perspectives on the same phenomenon, each useful in different contexts. Humidity is complex, not a single simple number, but a relationship between temperature and moisture, a shifting variable that affects everything from comfort to weather patterns. Frost heave is a phenomenon where soil expands when it freezes, pushing objects upward. It happens when water in the soil freezes, expanding by about 9%, exerting pressure on anything above it. Rocks, fence posts, building foundations, anything embedded in soil can be lifted by frost heave during freezing weather. Over multiple freeze-thaw cycles, objects gradually move upward, which is why rocks seem to rise to the surface in fields, why fence posts tilt after winters, why foundations crack. Frost heave is also why roads in cold climates develop potholes. Water seeps into cracks in the pavement, freezes, expands, breaking the pavement further, and then melts, leaving a larger crack that fills with more water, continuing the cycle. Frost heave is ice as a construction force, cold as movement, winter actively reshaping the landscape. It's slow, incremental, invisible day to day, but dramatic over seasons and years. Frost heave is physics at work, water's unusual property of expanding when frozen, creating forces strong enough to move rocks and buckle roads. A reminder that ice is powerful, that freezing is an active process, not just stillness. Microbursts are intense downdrafts from thunderstorms that hit the ground and spread outward in all directions, creating winds that can exceed 100 miles per hour. They're dangerous to aircraft because they create sudden wind shear. The plane encounters a strong headwind, then flies through the center where wind is downward, then encounters a strong tailwind, all within seconds, potentially causing loss of lift and control. Several aviation disasters were caused by microbursts before they were well understood and detection systems were developed. Microbursts are localized, typically less than 2.5 miles across, and brief, lasting just a few minutes. But in that time and space, they're extraordinarily violent, capable of snapping trees, destroying buildings, creating damage that looks like tornado damage but in a different pattern, divergent rather than convergent, radiating outward from a central point. Microbursts are falling air made dangerous, gravity and temperature difference conspiring to create sudden violence. A reminder that thunderstorms aren't just lightning and rain, but complex three-dimensional systems with winds moving in all directions. Downdrafts as intense as updrafts, capable of producing hazards at every scale from tiny hailstones to massive wind bursts. Sea breezes and land breezes are daily wind patterns in coastal areas, driven by differential heating. During the day, land heats up faster than the ocean. Warm air over land rises, and cooler air from over the ocean flows in to replace it. That's the sea breeze, onshore flow bringing cooler temperatures and sometimes fog or moisture. At night, the pattern reverses. Land cools faster than water. Air over the ocean is now warmer and rises, and cooler air from land flows out to sea. That's the land breeze, offshore flow. These breezes are gentle, typically 10 to 15 miles per hour, but they're reliable, happening almost daily in calm weather, creating a rhythm to coastal weather that locals intuitively understand. Sea breezes moderate coastal temperatures, keeping beaches cooler on hot days, which is why coastal areas often have smaller temperature ranges than inland areas at the same latitude. Land and sea breezes are miniature circulation systems, daily cycles of heating and cooling creating winds that oscillate back and forth, breathing patterns of the coastline, evidence that weather happens at all scales, that even small temperature differences create motion, create wind, create weather. The ozone hole is often misunderstood as a hole in the atmosphere, but it's actually a seasonal thinning of the ozone layer over Antarctica. During the southern winter, extremely cold temperatures allow polar stratospheric clouds to form. Chlorine and bromine from CFCs accumulate on these clouds, and then when spring arrives and sunlight returns, chemical reactions break down ozone rapidly, creating the hole, really a region where ozone concentration drops dramatically. As spring progresses, the hole closes, ozone concentrations recover, until the next winter when the process repeats. Thanks to the Montreal Protocol banning CFCs, the ozone hole is gradually getting smaller and is expected to fully recover by mid-century. But it's a reminder that human activity can have planetary scale effects, that chemistry doesn't respect borders, that substances released on one continent can affect atmospheric processes over another, that the atmosphere is a commons, shared by all, vulnerable to misuse, and also capable of recovery, if action is taken. The ozone hole is both warning and hope, evidence of damage and evidence of successful international cooperation to reverse it. Raindrops create ripples when they hit water surfaces, and those ripples spread outward in concentric circles, carrying energy, disturbing the surface. But raindrops also do something less visible. They create tiny bubbles underwater as they impact. These bubbles rise to the surface and burst, releasing sounds. This is part of what you hear during rain. The impacts, yes, but also the countless tiny bubbles forming and popping, creating a texture to the sound, a complexity that makes rain sonically interesting rather than just rhythmic noise. Rain on different surfaces sounds different, on leaves, on pavement, on metal roofs, on water. Each material responds differently to impact, creating different acoustic signatures. Rain is percussion, millions of drum beats per second, orchestrated by nothing but gravity and condensation, creating soundscapes that are chaotic but somehow soothing, white noise that isn't white, that has structure and rhythm and variation, that fills acoustic space without being overwhelming. Listening to rain is listening to weather in its most intimate form, each drop a note in an ongoing composition that never repeats exactly, but always sounds familiar. The Great Plains of North America experience some of the most variable weather in the world because they're a battleground where air masses collide. Cold, dry air from Canada, warm, moist air from the Gulf of Mexico, and dry air from the southwest all meet over the plains, and their interactions create dramatic weather. Severe thunderstorms, tornadoes, blizzards, droughts, floods. The flatness of the terrain means there are no mountains to disrupt air flow, so air masses can travel long distances and clash violently when they meet. This is why Tornado Alley exists. The specific geography and positioning create ideal conditions for severe weather. Plains residents experience temperature swings that would be shocking elsewhere. 70-degree days in February, blizzards in April, sweltering heat in summer, bitter cold in winter. The weather is unmoderated, extreme, offering little middle ground. Living with plains weather means accepting variability, expecting the unexpected, understanding that next week's weather might be completely different from this week's, not because of unusual circumstances, but just because that's how weather works in a place where competing systems meet. Static electricity is more common in winter because cold air is dry, and dry conditions don't conduct electricity away as efficiently as humid conditions. In summer, moisture in the air allows static charges to dissipate gradually. In winter, charges build up until they're released suddenly as a spark, the shock you feel touching a doorknob after walking across carpet. This is essentially miniature lightning, the same principle operating at vastly different scales. You're building up a voltage difference between yourself and your environment, and when you touch a conductor, current flows suddenly to equalize the charge. It's uncomfortable but harmless at the voltage levels involved. But it's a reminder that electricity is everywhere, that weather and climate affect even household phenomena, that the moisture content of air influences countless small aspects of daily life. Dry air creates static cling, shocks, flyaway hair. Humid air prevents all of that by allowing charges to dissipate constantly, invisibly, keeping everything at a similar voltage. Humidity is an electrical buffer, and its absence makes winter not just cold but also shockingly electric. Altitude sickness happens when you ascend to high elevations faster than your body can adapt to lower oxygen levels. Air pressure decreases with altitude, which means there are fewer oxygen molecules per breath. At 10,000 feet, the air pressure is about 70% of sea level. At 18,000 feet, it's roughly half. Your body can adapt by producing more red blood cells to carry oxygen more efficiently, but this takes days or weeks. If you ascend too quickly, you may experience headache, nausea, fatigue, shortness of breath, symptoms of altitude sickness. Severe cases can be life-threatening. This is a direct example of how atmospheric pressure affects human physiology, how weather, or at least one component of it, has immediate biological effects. People who live at high altitudes are adapted, with larger lung capacity and more efficient oxygen use. Lowlanders visiting mountains notice the thin air immediately, struggling to catch their breath, feeling their heart race, experiencing firsthand what the atmosphere is like at altitude. Altitude sickness is the body protesting atmospheric conditions it's not designed for, a reminder that we're adapted to specific environmental conditions, and that venturing outside those parameters has consequences. Weather affects mood, and research supports what people have long suspected. Sunny days correlate with better moods, while prolonged gray, rainy weather can contribute to low mood or even seasonal affective disorder. Light levels influence circadian rhythms and serotonin production, so reduced daylight in winter, especially at high latitudes where days are very short, can trigger depression in susceptible individuals. Barometric pressure changes may also affect mood, though mechanisms are less clear. Temperature matters too. Extreme heat makes people irritable, while moderate, comfortable temperatures are associated with better mood and cognitive performance. Weather is not destiny. Plenty of people are happy in gray, rainy climates and miserable in perpetual sunshine. But it's a variable, an influence, part of the context in which we experience life. Weather shapes not just external conditions but internal states, affecting neurotransmitters, sleep quality, energy levels, willingness to socialize. Understanding this doesn't give us control, but it gives us perspective, recognizing that some of what we feel is influenced by atmospheric conditions outside our control. And that's okay. Just another variable to account for, another factor in the complex equation of human experience. Permafrost is ground that remains frozen year-round, found in polar regions and high mountains. The top layer may thaw during summer, but beneath that, soil and rock remain frozen, sometimes to depths of thousands of feet. Permafrost contains organic matter, dead plants and animals, that has been frozen for millennia, preserved because decomposition requires liquid water and temperatures above freezing. As permafrost thaws due to warming temperatures, this organic matter decomposes, releasing carbon dioxide and methane, potent greenhouse gases, creating a feedback loop. Warming causes thaw, thaw causes emissions, emissions cause more warming. Permafrost also affects infrastructure. Buildings and roads built on permafrost can collapse if it thaws, losing the stability it provided when frozen. Permafrost is frozen time, ancient carbon storage, a component of the climate system that has been stable for thousands of years, but is now becoming unstable. It's a reminder that climate systems include slow-moving components that don't change noticeably year to year, but that, over decades, can shift dramatically, altering carbon cycles and landscape stability in ways that cascade through ecosystems and human communities. Rain shadows are dramatic examples of how mountains create climate. The Olympic Peninsula in Washington state illustrates this beautifully. The western side receives over 100 inches of rain per year, creating temperate rainforest, while areas just 30 miles east receive less than 20 inches, qualifying as semi-arid. The mountains wring out moisture from Pacific storms, leaving the leeward side dry. This pattern repeats around the world. Wherever mountains intercept moisture-laden winds, one side is wet and the other dry. The effect is so strong that it creates desert conditions in regions that, based on latitude, should be much wetter. The Patagonian desert exists because the Andes block moisture. Parts of Tibet are dry because the Himalayas block monsoon moisture. Rain shadows are mountains imposing their will on climate, geography dictating weather, topography creating boundaries between abundance and scarcity. And these boundaries are sharp. Drive through a mountain pass and watch the landscape transform from lush to arid within miles. Rain shadows are proof that climate is local, that global patterns are modified by terrain, that you can't understand a region's climate without understanding its geography. The coldest clouds are at the highest altitudes. Cloud-top temperatures in severe thunderstorms can reach -80 degrees Fahrenheit or colder. These clouds have built so high that they've reached the lower stratosphere, where temperatures are extreme. Meteorologists use infrared satellite imagery to measure cloud top temperatures, and extremely cold cloud tops indicate powerful storms with strong updrafts, which correlate with severe weather potential, large hail, tornadoes, damaging winds. The colder the cloud top, the more intense the storm generally. It seems counterintuitive that cold indicates intensity, but it's about altitude. Reaching extremely high means the updrafts are powerful, which means the storm has enormous energy, which means it can produce severe weather. Cloud top temperature is a diagnostic tool, a way to assess storm strength from space, translating infrared radiation into information about storm structure and potential hazards. The coldest clouds are also the most dangerous. Paradoxically, their icy tops warning of violence below. Weather stations have standardized measurements, temperature recorded at 5 feet above ground in a ventilated shelter to avoid direct sunlight, precipitation measured in rain gauges that minimize splashing and evaporation, wind measured at 33 feet above ground in open terrain. These standards exist so that measurements from different locations are comparable. But they also mean that official weather measurements don't always match your experience. The temperature in the official weather shelter might be 75 degrees, but in direct sunlight on dark pavement, it might feel like 100. Wind at 33 feet above ground is stronger and steadier than at ground level where you're walking. Precipitation measurements assume certain gauge types and locations. Official weather data is real and useful, but it's also abstracted, standardized, representing idealized conditions rather than your specific experience at your specific location. Weather is hyperlocal, varying over distances of feet and minutes, and no official measurement can capture that variability. Weather reports give you general conditions. Your body tells you specific conditions. Both are valid, different perspectives on the same atmospheric state. Snow insulates so effectively that igloos can maintain interior temperatures 60 degrees warmer than outside air without any heat source beyond body warmth. The snow blocks wind, and the air trapped in and between snow blocks provides insulation. The dome shape minimizes surface area relative to volume, reducing heat loss. Igloos are elegant architecture, using the properties of snow itself to create shelter from snow, turning the environment into protection from the environment. Other animals use snow for insulation too. Voles and other small mammals create tunnel systems under the snow, living in the subnivean zone where temperature is relatively stable, protected from both cold air and predators. Snow becomes habitat, a layer that certain ecosystems depend on. When snow cover is absent or inconsistent due to warming temperatures, these animals struggle, losing the insulation they've adapted to. Snow is not just precipitation, but also insulation, habitat protection, a material with properties that shape ecological relationships and make survival possible in conditions that would otherwise be lethal. Breathe gently. Let your awareness rest wherever it wants to rest, on these words, on the sound of your own breathing, on nothing in particular. The journey through weather facts continues, but there's no obligation to follow every word, no requirement to stay alert. Weather happens whether we're paying attention or not, and these facts will continue unfolding whether you're awake or asleep. Rest is welcome here. Drifting is encouraged. Let go of any remaining effort and simply be. All is well. All has always been well. Chinook winds, also called Furhan winds, are warm, dry winds that descend mountain slopes. As air rises up the windward side of a mountain, it cools and releases moisture as precipitation. Then, as the air descends the leeward side, it warms. And it warms faster than it cooled because it's now drier, having lost moisture. The result is wind that arrives at the base of the mountain warmer than it was at the equivalent altitude on the other side. Chinooks can raise temperatures dramatically and quickly, 30 or 40 degrees in a few hours. In winter, a Chinook can bring temporary relief from cold, melting snow, creating spring-like conditions in the middle of January. Indigenous peoples of the Great Plains name these winds. They recognized their arrival and their effects, knew that the warm wind from the mountains meant relief from winter's harshness, at least temporarily. Chinooks are mountain winds, geography converting moisture to heat, altitude and temperature gradients creating local weather phenomena that can dominate conditions for days, overriding the broader regional pattern with hyperlocal warmth. Weather forecasting has improved dramatically over recent decades. In the 1970s, a 3-day forecast was about as accurate as a 6-day forecast is now. Improvements come from better satellite data, more powerful computer models, denser observation networks, and improved understanding of atmospheric physics. But there's a limit to predictability, articulated by Edward Lawrence's chaos theory research. Weather is a chaotic system, meaning small differences in initial conditions lead to large differences in outcomes over time. This is the famous butterfly effect. No matter how good our models become, there's a theoretical limit to how far ahead we can forecast accurately, probably around 2 weeks for specific conditions at specific locations. We can make longer-range forecasts about general patterns, whether a month will be warmer or wetter than average, but not specific day-to-day weather. Weather forecasting is an exercise in working with uncertainty, using probability, giving ranges rather than single values. It's science acknowledging its limits, prediction constrained by chaos, the atmosphere demonstrating that some things are inherently unpredictable beyond certain time horizons. Hoarfrost is different from regular frost. It forms when water vapor in the air deposits directly onto surfaces as ice crystals. But instead of the flat, fern-like patterns of regular frost, hoarfrost grows as spiky needles or feathery structures, often pointing into the wind. Hoarfrost requires specific conditions, sub-freezing temperatures, high humidity, and often fog or mist. The ice crystals grow larger and more elaborate than regular frost, sometimes creating fairy tale landscapes where every twig and blade of grass is coated in delicate ice needles. Hoarfrost is fragile, melting or sublimating as soon as sunlight touches it or temperatures rise even slightly. It's more common in certain environments, near rivers, in valleys where cold air pools, in places where moisture is abundant, and temperatures are consistently below freezing. Hoarfrost is ice as art, vapor becoming solid in intricate forms, temporary sculptures growing overnight, transforming the ordinary landscape into something otherworldly, and then vanishing, returning to invisibility, leaving no evidence they ever existed except perhaps in photographs or memory. The hygrometer measures humidity, and early versions were surprisingly clever. Human hair changes length with humidity. It becomes slightly longer when humid and shorter when dry. Hair hygrometers use this property, attaching a strand of hair to a mechanism that would move a pointer as the hair lengthened or shortened, indicating humidity changes. These were accurate enough for general purposes and required no power source, just a strand of hair and mechanical linkage. Modern hygrometers use electronic sensors, but the principle remains, measuring some property that changes reliably with moisture content and translating that change into a number. Humidity is invisible, but its effects are measurable, and humans have been measuring it for centuries, finding ways to quantify the unquantifiable, to give numbers to sensations, to make the invisible visible through instruments and ingenuity. Weather measurement is part of humanity's long project of understanding the environment, translating sensory experience into data, making predictions, exerting a small measure of control through knowledge if not through power. Waterspouts are tornadoes over water, similar in structure but typically weaker than land tornadoes. They form over warm water when conditions are right, instability, moisture, rotation. Waterspouts can be spectacular, a rotating column connecting water surface to cloud base, spray spiraling upward, the water beneath visibly disturbed. Most waterspouts are relatively weak, dissipating quickly if they move onshore, but they're hazardous to boats and swimmers. Fairweather waterspouts form differently from tornadic waterspouts. They develop in relatively calm conditions, growing downward from cumulus clouds rather than forming from supercell thunderstorms. They're more common in tropical and subtropical waters, particularly in the Florida Keys, where conditions favor their formation. Waterspouts are weather's way of demonstrating that the same processes work over water and land, that tornadoes aren't dependent on ground friction or terrain, that rotation and instability can create vortices anywhere conditions allow. They're beautiful and dangerous, weather made vertical and visible, energy concentrating into a narrow column, spinning water and air into temporary unity. The dew point spread is the difference between air temperature and dew point temperature, and it tells you how close the air is to saturation. A small spread, say temperature 70 and dew point 68, means the air is nearly saturated, and any slight cooling will cause condensation, fog, or dew. A large spread, temperature 70 and dew point 45, means the air is dry, far from saturation. Pilots pay attention to dew point spread, because when it's small, fog can form rapidly as temperature drops, reducing visibility. Meteorologists use it to assess potential for thunderstorm development. A small dew point spread means plenty of moisture is available, fuel for storms. Dew point spread is a diagnostic number, a way to quantify how moist the air is relative to its temperature, translating two measurements into useful information about what's likely to happen next. It's another example of weather being quantifiable, of atmospheric conditions being expressible as numbers that, once you understand them, tell stories about fog and dew and storms and humidity, about the invisible moisture content of seemingly empty air. Snowflakes take many different forms depending on the temperature and humidity conditions they experience while forming. At temperatures just below freezing, snowflakes tend to be flat plates. Colder temperatures produce columns or needles. Very cold temperatures create prisms, and at the coldest temperatures, snowflakes become simple hexagonal plates again. There's a diagram called the Nakaya diagram, after Japanese physicist Yukihiro Nakaya, that maps snowflake shapes to temperature and humidity, showing the specific conditions that produce each type. This means that if you examine a snowflake carefully, you can deduce something about the atmospheric conditions where it formed. Each snowflake is a record, a tiny atmospheric probe that sampled conditions aloft and crystallized those conditions into structure. Snowflakes are data, frozen information, whether encoded in ice. And the variety is stunning. Stellar dendrites, sector plates, hollow columns, capped columns, fern-like stellar dendrites. Each type with its own formation conditions, its own signature appearance, contributing to the truth that no two snowflakes are alike because no two follow exactly the same path through exactly the same conditions. The lowest layer of the atmosphere, the troposphere, contains about 80% of the atmosphere's mass and nearly all of its water vapor. It's where weather happens, where clouds form, where we live and breathe. The troposphere extends from the surface to about 7 miles at the poles and 12 miles at the equator. It's thicker at the equator because warmer temperatures cause the atmosphere to expand. Above the troposphere is the stratosphere, then the mesosphere, thermosphere, and finally the exosphere, fading into space. But most of what we call the atmosphere, the part that matters for weather, for climate, for life, is that first few miles, the troposphere. It's a thin shell, a delicate boundary layer wrapped around the planet, all that separates the surface from the vacuum of space. The troposphere is home, the layer we're adapted to, the region where pressure and oxygen and temperature are compatible with human life. Above it, conditions become increasingly hostile, too cold, too little oxygen, too little pressure. The troposphere is where weather happens, where life happens, a narrow zone of habitability on a rocky planet hurtling through space. Lightning can travel upward from the ground to the clouds, not just downward from clouds to ground. What usually happens is this. Negative charge builds in the cloud and sends a stepped leader downward, branching as it descends. When it gets close to the ground, positive charge in the ground reaches upward in streamers. When the descending leader connects with an upward streamer, a circuit completes, and a return stroke travels upward, much brighter than the initial leader. That bright return stroke is what you see as lightning. It's actually traveling from ground to cloud, even though the process started with a downward leader. Lightning is bidirectional, an exchange between earth and sky, charge flowing in both directions to achieve equilibrium. And sometimes, from tall structures like skyscrapers or mountaintops, lightning initiates from the ground upward without a descending leader starting it. Upward lightning is more common from tall structures and at high elevations. Lightning is flexibility, energy finding the easiest path between charge centers, indifferent to direction, only interested in neutralizing the voltage difference. The word weather comes from an Old English word meaning wind, storm, tempest, but over time it came to mean atmospheric conditions generally. Climate comes from a Greek word meaning slope or inclination, referring to the angle of the sun's rays at different latitudes, which determines how much solar energy different regions receive. Weather is what's happening now. Climate is the average of what happens over decades. Weather is mood. Climate is personality. You can't judge climate from a single weather event any more than you can judge someone's personality from their mood on one particular day. A cold winter doesn't disprove climate warming any more than a hot day proves it. Climate is the long-term pattern, the trend, the average of countless weather events smoothed over time. Weather is immediate and specific. Climate is abstract and statistical. Both are important, both are real, but they operate on different timescales and require different kinds of thinking to understand. We experience weather, we analyze climate, we feel weather, we measure climate. Understanding the distinction is essential for making sense of atmospheric science. Frost flowers are extraordinary ice structures that form on new sea ice when the ice surface is much colder than the water below. Water vapor sublimates from the ice surface, and due to the extreme temperature difference, it immediately freezes into delicate, flower-like structures, layers and petals of frost growing vertically from the ice. Frost flowers are fragile, hollow, and remarkably beautiful, but they're also scientifically interesting because they concentrate salt and other substances from the sea ice, creating pockets of highly saline material. They exist in polar regions, forming on newly frozen sea ice during calm, extremely cold conditions. They last only until wind or warmth destroys them, or until snow covers them. Frost flowers are the ocean's exhalation frozen in mid-breath, vapor becoming ice in forms that resemble botanical structures, even though they're purely physical chemical phenomena. They're another example of nature creating beauty as a side effect of physics, temperature and phase change producing forms that seem intentional but are just the inevitable result of molecules following the lowest energy path available to them. And now, we've reached the end of this gentle collection of weather and climate facts. We've traveled through snow and rain, through clouds and winds, through heat and cold, exploring the atmosphere and its endless variations. Weather is happening right now, outside your window, above your head, across the planet. Clouds forming, winds blowing, temperatures shifting, moisture cycling. It's the background hum of life on Earth, the atmospheric conditions that make existence possible, that shape ecosystems and influence mood and determine what we wear and whether we carry an umbrella. Weather is ordinary and extraordinary, familiar and mysterious, understood and still full of surprises. And now you know a little more about it, or perhaps you've drifted off to sleep and haven't heard these last words at all, which is perfectly fine. The weather will continue, indifferent to whether we're paying attention, doing what it's done for billions of years, cycling and circulating, distributing energy and moisture, making Earth the livable, beautiful, endlessly interesting place that it is. And so we come to the end of our journey through the atmosphere, through weather and climate, through the science of the air around us. If you're still awake, thank you for staying with me. If you've drifted in and out, that's wonderful. That's exactly what this space is for. And if you've fallen asleep entirely, well, you won't hear this, but I hope you're resting deeply, peacefully, you're breathing slow and steady, your mind quiet. Weather is with us always. It's the context of our lives shaping our plans, influencing our moods, determining what grows and what withers, what freezes and what melts. We live at the bottom of an ocean of air, and that air is constantly moving, constantly changing, responding to the sun's energy, to the planet's rotation, to the distribution of land and sea. Weather is the atmosphere's ongoing conversation with itself, adjusting and readjusting, seeking balance, never quite achieving it because conditions are always changing, energy always flowing, heat always moving from hot to cold, moisture always cycling from ocean to air to land and back again. What I hope you take from tonight's exploration, whether you remember specific facts or just the feeling of calm, gentle learning, is a sense of wonder. Weather isn't just something that happens to you, something to complain about or celebrate depending on how it affects your plans. Weather is a window into how the planet works, into the physical laws that govern gases and liquids and energy. Every raindrop, every snowflake, every cloud, every gust of wind is physics in action, mathematics made tangible, science you can feel on your skin and see in the sky. And there's comfort in that, I think. Comfort in knowing that weather, for all its apparent chaos and unpredictability, follows rules. Not the kind of rules you can exploit to control it, but rules nonetheless. Equations describing how air pressure affects temperature, how moisture condenses, how energy flows. Weather is comprehensible, even when it's complex. Scientists can model it, predict it within certain limits, explain why it does what it does. We've turned the sky from a realm of gods and omens into a subject of study, and in doing so, we haven't made it less wondrous. If anything, understanding weather makes it more remarkable, not less. So tomorrow, when you step outside, maybe take a moment to notice the weather. Feel the air temperature. Observe the clouds if there are any. Notice the wind, its direction and strength. Feel the humidity. You're experiencing the atmosphere, sensing its state, participating in the same system that creates hurricanes and dew and snowflakes and auroras. You're part of weather, not separate from it. Your body exchanges heat with the air, evaporates moisture into it, breathes it, depends on it. You are embedded in the atmosphere, a participant in the ongoing exchange of energy and matter that we call weather. Thank you for spending this time with me, for exploring the calm corners of atmospheric science, for making space in your evening for learning and for rest. If you enjoyed this journey and you'd like to take more like it, consider subscribing, consider liking the video, consider sharing it with someone else who might appreciate a gentle way to drift into sleep. But truly no pressure. You've been here, you've listened, and that's enough. Sleep well. Rest deeply. Let the weather outside do its work. Clouds forming, winds blowing, temperatures shifting through their nightly cycles. While you rest, safe and warm, your breathing slow and even, your mind finally quiet after the long day. The atmosphere will still be there tomorrow, still cycling, still creating weather, still offering endless opportunities for wonder. But for now, just rest. Good night.